Building agents that can plan, reason, and execute at scale is the next frontier in AI systems. This part covers how to design agents that decompose complex goals into actionable steps, reason over constraints, and coordinate execution across distributed resources. A static prompt gives the agent a fixed set of instructions, but the real world changes. Agents that never update their knowledge or strategy get stuck repeating the same mistakes. Learning loops let the agent adapt by incorporating feedback from each interaction, so it improves over time instead of staying frozen. A static prompt can produce a surprisingly capable answer in a single forward pass, but that answer is a snapshot, not a system. This section explains why static prompting works well for narrow tasks and where it breaks down when the situation changes. A static prompt is fast, understandable, and often good enough when the task is narrow, well-specified, and mostly read-only. But it captures what the model should say in one turn, not how the system should adapt when a tool fails, a constraint appears late, or an early assumption turns out to be wrong. For an agent, that distinction matters more than it does for a chat assistant, because an agent is expected to decide, act, observe, and continue under uncertainty. Imagine the Atlas Travel Assistant being asked to book a weekend trip with a budget ceiling, a preferred airport, and a strict no red-eye constraint. A static prompt can encourage a neat itinerary, but the quality depends on the prompt anticipating every important condition in advance. If the user later adds a hotel loyalty preference or a flight option disappears, the prompt itself has not improved. The system can only generate another answer from the same fixed instruction set. A script can be polished and predictable, and for many bounded tasks, that predictability is exactly what you want. Yet a script is different from a system that can inspect its own progress and choose whether to continue, branch, or abort. In practical agent work, the ability to revise is often more valuable than a marginal improvement in fluent wording. The real question is whether the system can produce a plan that survives contact with partial information, changing conditions, and downstream constraints. The figure contrasts static prompting on the left with an agentic learning loop on the right. On the left, a single arrow goes from prompt to answer. One shot, no feedback. On the right, the loop shows observation, revision, and continuation as new information arrives. That loop is what makes an agent resilient where a static prompt is brittle. A model may generate an elegant first response, but fail to keep track of constraints across a multi-step interaction or make inconsistent choices when a tool returns unexpected data. In the travel setting, this might look like recommending a flight before checking visa requirements, or ignoring a hotel cancellation policy that makes the apparent cheapest option expensive in practice. The output can read well, while the underlying behavior remains untrustworthy. That is why the natural unit of improvement for agents is not the isolated answer, but the decision process that produces it. The core idea is that when we evaluate an agent, we should look at the entire sequence of steps it took, not just the final answer it produced. That sequence is called a trajectory, and it reveals how the system behaved, not just what it said at the end. A good final answer produced by a lucky chain of guesses is very different from the same answer produced by a careful sequence of checks, revisions, and confirmations. In ordinary text generation, the output is often all that matters. In agent systems, the path matters because it determines reliability, recoverability, and the cost of failure. If the model takes a detour but notices the mistake and corrects it, the trajectory may still be healthy. If it reaches the right destination by accident while skipping crucial validation, the final text can be misleadingly reassuring. This diagram shows two different paths that end at the same final answer. The top trajectory includes a step where the agent checks its work and corrects a mistake. The bottom trajectory skips that validation and just happens to land on the right answer. Only by looking at the full sequence can you tell which agent is robust and which one got lucky. It is tempting to judge only the final sentence a travel assistant produces, like here is the best itinerary. But from the perspective of agent design, that sentence is just the surface. The system may have searched multiple flight combinations, queried a booking tool, encountered a conflicting constraint, and then rerouted to an alternative hotel. Those intermediate steps are not incidental. They are the evidence of whether the agent can operate as a controlled process rather than as a one-off generator. Most of the failure modes that matter arise in the middle. Forgotten constraints, incomplete retrieval, stale assumptions, or an unacknowledged dead end. A trajectory can expose whether the agent explored enough alternatives, whether it recovered from a failed tool call, whether it handled uncertainty conservatively, and whether it took unnecessary risky actions before checking its assumptions. Two trajectories can end with the same destination but have radically different operational quality. One may be robust and transparent. The other may be lucky and opaque. If you optimize only the visible answer, you risk rewarding the wrong behavior. If you optimize the trajectory, you can teach the system not just to finish, but to finish well. The useful question is not only was the final result good, but which decisions along the way deserve credit, and which ones introduced unnecessary risk or waste. This matters because the model's future behavior depends on what parts of a sequence are treated as successful. A system that always gets praise for the final destination, regardless of route, has no incentive to learn better navigation. A system that is judged on the path can learn that some trajectories are more dependable than others, even when the endpoint is the same. That is the basis for the learning methods later in the chapter. Travel planning is naturally sequential, constraint-heavy, and full of trade-offs. A first-pass answer can look reasonable if it simply optimizes one visible dimension, yet still fail on hidden constraints that matter operationally. That makes travel planning a clean illustration of why one-shot prompting is not enough. Consider a bounded request. Atlas is asked to propose a 3-day trip that stays within budget, arrives before a meeting, and avoids overnight airport connections. A static prompt may lead to a polished itinerary with a cheap fare and the convenient hotel. But if the itinerary ignores a late change in flight availability, the answer is stale. If it misses the hotel's cancellation penalty, the apparent savings are fake. If it chooses a connection that barely fits on paper, the plan may be fragile under ordinary delay risk. A revised trajectory, by contrast, can inspect the failed option, compare two backups, and select the more robust path, even if it is not the lowest nominal price. The value comes from revision, not from the elegance of the first draft. The same example reveals why bounded autonomy matters. Atlas does not need open-ended freedom to do everything. It needs enough autonomy to recover from incomplete information and enough structure to stay within policy. In practice, that means the agent should be able to say, in effect, this route satisfies the time constraint but creates a hidden risk, so I will search again, or the best available option now requires approval, so I will pause before committing. That ability is not a luxury. It is what separates an agent from a deterministic response template. A travel assistant that can adapt within a governed boundary is more useful than a system that sounds certain while quietly ignoring instability in its own plan. This example also helps separate the final answer from the full decision trajectory. The final itinerary is only the visible artifact. The better question is whether the agent discovered the right trade-off by deliberate comparison or merely emitted a plausible summary after minimal checking. A trajectory that begins with an appealing but invalid option, then revises after tool feedback, may be superior to a trajectory that never explored alternatives in the first place. That is why later methods in this chapter pay attention to samples, rollouts, rankings, and search. They are mechanisms for improving the path, not just decorating the destination. This example also helps separate the final answer from the full decision trajectory. The final itinerary is only the visible artifact. The better question is whether the agent discovered the right trade-off by deliberate comparison or merely emitted a plausible summary after minimal checking. A trajectory that begins with an appealing but invalid option, then revises after tool feedback, may be superior to a trajectory that never explored alternatives in the first place. That is why later methods in this chapter pay attention to samples, rollouts, rankings, and search. They are mechanisms for improving the path, not just decorating the destination. A learning loop is the process that turns outcomes into better decisions over time. This part explains how feedback from actions shapes an agent's future behavior and why that makes agentic systems fundamentally different from static programs. At its simplest, a learning loop works like this. The system acts, the action produces an outcome. That outcome generates feedback, and the feedback influences what the system does next. The feedback can come from a user, a judge model, a tool result, a simulator, or an environment that rewards success and penalizes failure. The key is that the agent is not stuck repeating the same pattern. It can improve because its own experience shapes its future decisions. A static prompt specifies behavior once and never changes. A learning loop creates a mechanism for behavior to improve across repeated experiences. In the travel example, Atlas might fail on a booking attempt, learn that a particular sequence of checks is brittle, and prefer a more robust path next time. The improvement can happen during training, where the policy itself is updated, or during operation, where the system learns which branches to revisit. The important point is the direction of causality. Outcomes influence future policy. This causality is why these systems feel different from ordinary software. Traditional software follows rules written ahead of time. Agentic systems still rely on rules, but they also incorporate adaptive selection based on feedback. The closest analogy is a navigator that updates its route after inspecting the road ahead. The route is not determined solely by the original plan. It is refined by what the system discovers while moving. The practical payoff is resilience. When conditions change, the system can adjust rather than merely fail. This is where the chapter begins to separate learning from execution. Learning alters future behavior based on experience. Execution applies the current behavior under current constraints. In many real systems, these are intentionally decoupled. An agent may execute a policy today, log what happened, and only later use those records to improve tomorrow's policy. Or it may keep the same policy and devote additional inference time, compute, to revising the current decision. Both are forms of improvement, but they occur on different timescales and serve different operational goals. Keeping that boundary clear will matter when we discuss ranking, search, and workflow-level learning. A good final outcome does not always mean the decisions along the way were good. Trajectory-level credit assignment looks inside the path to separate genuine skill from accidental success. If a travel assistant picks a bad route, but recovers only because a backup option happened to be available, the final itinerary is still successful. Rewarding that trajectory the same as a carefully planned one teaches the system to rely on luck rather than robust reasoning. When multiple paths lead to the same endpoint, a hidden dead end or a constraint violation narrowly avoided by chance may reveal that the policy is not actually reliable. Trajectory-level judgment lets the system prefer paths that are stable, efficient, and policy compliant, not just successful. A governed travel workflow might include an early pause for approval, a deliberate comparison of alternatives, and a conservative choice under uncertainty. A reckless trajectory that produces the same itinerary while violating policy or wasting compute should not be treated as equivalent. Trajectory-based methods formalize this. The path itself is a unit of behavior, and its internal quality matters as much as the endpoint. If the system learns from poorly chosen signals, it may optimize the visible surface while degrading the process underneath. For example, sounding confident rather than checking constraints. A trajectory-level lens does not solve these problems by itself, but it creates the right target for improvement. Not all improvement in agent systems works the same way. There are two fundamentally different levers: training time learning, which updates the model's parameters, and test time search or refinement, which spends more computation during decision-making while keeping the model fixed. Understanding this distinction clarifies how real systems get better. Training time learning updates the model parameters based on experience, so the agent becomes permanently better at similar tasks in the future. Test time search, on the other hand, leaves the model unchanged but spends extra compute to explore alternatives before committing to a decision. These are related strategies, but they serve different purposes and are not interchangeable. Consider Atlas choosing between two itineraries. A simple one-pass policy might grab the first plausible option and move on. A test time refinement loop, however, can generate both candidates, check constraints, compare trade-offs, and only then commit. The model hasn't become smarter permanently, but it has become more deliberate in that moment. That extra deliberation can dramatically reduce avoidable mistakes, especially when uncertainty is local and checking costs less than an error. Training time learning is the better choice when the same failure patterns recur across many tasks, because changing the policy can amortize the improvement over future requests. Test time search is better when you need better decisions right now, or when the problem is too variable to encode efficiently into parameters alone. In practice, serious agent systems use both, They train a better policy and still reserve additional compute for difficult decisions. The operational implication is that compute becomes a design parameter, not just a deployment cost. More compute at inference time doesn't create intelligence from nothing, but it can by deliberation, verification, and branch exploration. That's a different kind of capability from parameter scale. Think of it as a budget for caution. The more uncertainty or consequence attached to a decision, the more valuable it becomes to spend compute on checking alternatives before acting. Reinforcement learning provides a framework for turning outcomes into better decisions over time. This part of the chapter shows how that framework applies to LLM agents, especially when behavior needs to be optimized at the level of whole sequences rather than individual tokens. At its core, reinforcement learning gives a language for describing how outcomes shape future behavior. An agent chooses actions under a policy, observes the consequences, receives a signal about how good those consequences were, and then updates future behavior accordingly. For LLM agents, the key insight is that behavior can be optimized at the level of sequences rather than isolated tokens, a much more natural fit for tool using multi-step systems than plain next token prediction alone. It helps to think of RL here as a family of ideas rather than a single algorithm. The common thread is the same. Use feedback from the environment or judge to improve what the agent tends to do. That feedback can be sparse, arriving only at the end of a trajectory, or denser, attached to intermediate steps. The reward might come from a task outcome, a preference model, or a structured scoring function. The design intuition is stable. If the agent can act, observe, and adapt, then outcome-linked feedback becomes a natural way to improve it. For LLM agents, this matters because many failures are sequential rather than lexical. The problem is not always that the wording is bad. Often the issue is that the sequence of decisions was suboptimal. The model may have chosen the wrong branch, called the wrong tool, or failed to revisit a constraint after a tool response changed the situation. RL gives a formal path to improving decision behavior over time, especially when the desired behavior is hard to encode as a single supervised example, but easy to judge after the fact. The important thing here is the role RL plays in this chapter. It is the bridge between experience and improved behavior. Later sections will narrow this broad idea into specific methods for ranking, relative optimization, rollout generation, and search. For now, the key takeaway is that agents are not just responders. They're systems whose future responses can be shaped by past trajectories. Training changes the policy, but test time compute changes how the system decides around that policy. Both can improve quality, but they work differently, and understanding that difference is key to building capable agents. Instead of committing to the first output, a system can generate several candidates, evaluate them, revise them, or search over them before choosing. The model itself stays unchanged, but the output quality improves because the system has more opportunity to inspect and compare. In agent settings, spending a few extra seconds to compare options is often worthwhile if it avoids a costly mistake. For example, when selecting a hotel, checking cancellation policy, transit distance, and budget fit can surface a safer choice than a single greedy completion. Search also makes the system more robust when evidence is incomplete. Modern agent design treats inference as an active process. The agent can draft, inspect, branch, score, and revise before it acts. This is the conceptual foundation for tree-based search methods later in the chapter, where the system explores multiple futures and chooses among them rather than accepting the first plausible continuation. This is not a workaround for weak models. It gives you a way to balance speed against certainty. In low-stakes, high-volume settings, a lightweight one-pass path is enough. In high-consequence settings, deeper search can materially improve reliability. The right agent knows when additional thought pays for itself. This part of the chapter introduces three key methods: ART, ruler, and RLLM. Each one represents a different way to move from static prompting toward learning, ranking, and workflow-aware optimization. The core idea is that an agent's quality comes from its ability to improve over trajectories, not just from a single polished response. Art and ruler make the abstract idea of trajectory improvement concrete. Instead of treating the agent as a single completion, They frame it as a sequence of candidate behaviors that can be generated, judged, compared, and updated. This allows us to talk about quality in a richer way than just success or failure. A trajectory can be preferred, partially acceptable, risky, or inefficient, and those distinctions matter for making behavior more reliable over time. The key point is that the trajectory itself becomes the object of optimization. Later sections will show how such judgments become training signals. But for now, the important shift is from evaluating a single output to evaluating the entire sequence of actions and decisions that led to it. Our LLM takes the same intuition and extends it beyond the isolated agent policy to the workflow that surrounds it. Many production systems don't consist of a single free-form policy acting alone. They have staged workflows with branching, evaluation, escalation, and reuse. If the workflow itself can be learned or improved, the system can get better even if the underlying model stays the same. That's a powerful systems-level idea. Optimization doesn't have to stop at the model boundary. These names serve as signposts for where the chapter is headed, toward methods that use feedback, ranking, and structured execution to improve behavior at different scales. You don't need the mechanics, yet to appreciate the motivation. What matters is that the chapter will not treat prompting as the end of the story. It will treat prompting as the first layer in a larger stack of improvement loops. The goal for an agent system is not total freedom. It is bounded autonomy, enough room to adapt, but enough structure to stay controllable. That idea will guide everything in this chapter. An agent should be able to revise a trip plan when a flight gets canceled, but should not book an expensive hotel without asking first. The ideal agent knows when to act, when to pause, and when to ask for help. Continuous refinement is what keeps bounded autonomy from being too cautious. A system that observes its own trajectory, learns from feedback, and searches before acting can improve its decisions while staying within policy. That combination turns an LLM from a text generator into an agentic system. Execution uses the current policy to move through a workflow. Learning changes that policy over time. Search improves a single decision without permanently changing the policy. Keeping these three separate will make later sections on RL vocabulary, rollout generation, and tree search much clearer. Static prompting gives you a starting point. But learning loops, search, and workflow refinement give you an agent that adapts within bounds, recovers from friction, and improves as a system. That is the central message of this chapter. A plain prompt response model is too small for an agent that acts, observes consequences, and improves over time. Once an assistant does more than emit a single answer, the system is choosing actions, taking steps in an environment, and using feedback to shape future decisions. That is the territory of reinforcement learning vocabulary, even when the implementation is not a textbook RL algorithm. Think in three layers. A fixed script always follows the same phrasing and order, regardless of the trip. A live improviser reacts to what happens, but may not improve from the performance. An RL-trained agent is like a performer whose recordings are reviewed, scored, and fed back into later performances. The important difference is not spontaneity alone, but learnability. Atlas can search for flights, inspect constraints, compare options, and ask for approval. Those actions only become learning material if the system records what happened and attaches some notion of success or failure. That is why RL terminology matters. It names the mechanism by which experience becomes improvement. This distinction clarifies where learning ends and execution begins. During execution, the agent is simply following its current policy, gathering observations, and producing outputs. During training or search, those same executions become data, candidate behavior, or evidence. Later methods will rank whole paths, optimize groups of trajectories, or search over possible futures at test time. Keep this practical rule in mind throughout the chapter. If a system chooses actions, records what happened, and can improve from feedback on those choices, then RL language is usually the most accurate lens. It prevents every tool-using application from being mislabeled as just prompting, and it also prevents every feedback mechanism from being treated as a mysterious new paradigm. A single forward pass through a model produces a one-shot completion that is useful for answering questions, but it is not enough for building an agent. Repeated interaction changes the structure entirely. Each turn depends on the previous one, and each turn creates new evidence about whether the current behavior is good enough. In a repeated loop, the agent does not commit to one answer forever. It can act, observe the result, and adapt. Feedback may be immediate, like a tool call succeeding or failing, or delayed, like judging the final trip plan against user constraints. The learning value comes from the path taken, not just the final answer. Two agents might produce similar itineraries, but one carefully checked constraints while the other got lucky. This is where evaluation and learning diverge. In standard prompting, you ask whether the final response is correct. In an RL-oriented agent workflow, you care about whether the action sequence is robust, efficient, safe, and repeatable. A model that occasionally gets lucky on the final answer can still be a poor policy. For Atlas, a reliable behavior pattern is more valuable than a single correct guess. The key conceptual shift is that the model's output is no longer the endpoint. It is one move inside a longer game. Once execution becomes iterative, you need a language for the sequence of steps, the result of each step, the feedback attached to the sequence, and the update process that changes future behavior. Without that vocabulary, it is hard to distinguish a well-designed workflow from a genuine learning process. The key conceptual shift is that the model's output is no longer the endpoint. It is one move inside a longer game. Once execution becomes iterative, you need a language for the sequence of steps, the result of each step, the feedback attached to the sequence, and the update process that changes future behavior. Without that vocabulary, it is hard to distinguish a well-designed workflow from a genuine learning process. Reinforcement learning gives us a structured way to think about how an LLM agent interacts with its environment. The core idea is a loop of action, observation, and update, and we can map each part directly onto what an agent does. In this diagram, the agent starts with a context. That's the current state, including the user's request and any history. The policy chooses an action, which could be a response or a tool call. The environment then sends back an observation and a reward. Over time, the accumulated experience can be used to update the policy itself. At its heart, reinforcement learning is a loop. The agent acts, observes the result, and updates something based on that experience. For an LLM agent, an action might be generating a response, calling a tool, asking for clarification, or deciding to stop. The environment responds. For a travel agent, that could be search results, a booking confirmation, or a user's approval. The agent observes that result, incorporates it into its context, and decides what to do next. Over time, the accumulated experience becomes training data that can alter future behavior. The word update is easy to misinterpret. It does not mean the model must change its weights on every turn during deployment. In many production systems, the model weights stay fixed while the agent updates its internal state, selects a new route, or chooses among candidate trajectories. During training, the same loop can feed parameters, reward models, or preference models. The key point is that the loop is behavioral, not just conversational. Each action changes the future options available, and each observation changes the context the policy conditions on. The system is learning in a broad sense, even when the actual weight update happens later, offline, or in batches. Consider a trip planning request with a date range, a budget cap, and a preference for nonstop flights. The agent's first action might be to search for candidate flights. The observation is the return set of fares and durations. The agent then reasons about trade-offs, maybe calls a calendar tool to validate dates, and may ask for approval if the best option exceeds a spending threshold. Each of these steps is part of the loop. If one trajectory consistently forgets the budget constraint and another consistently honors it, the difference is not just in the final output. It is a difference in policy behavior across multiple observations. This view explains why RL is such a natural fit for agents. The agent's value is not just in answering correctly once, but in repeatedly choosing good actions under uncertainty. That means the system must treat the path as first class. The path exposes where the agent explored, where it hesitated, where it recovered, and where it failed. A model that can only emit final answers lacks a mechanism to learn from those distinctions. A model embedded in an action observation loop can turn them into improvements. Reward is the feedback that tells a learning system which behavior was better. It is the core signal that drives improvement in agent training. Reward is not just a pass or fail label. It can capture many things at once. Factual correctness, whether the agent followed policy, how efficient the actions were, or how satisfied the user might be. Sometimes the reward comes only at the end of a long sequence, sometimes after every step, and sometimes it is built from several different evaluators combined together. When rewards are delayed, the learning problem becomes harder. An agent like Atlas might call a search tool several times, filter results, and only produce a recommendation at the end. If the final plan is good, the reward attaches to the whole trajectory, not to any single step. The system then has to infer which earlier actions actually contributed to the success. A booking does not tell you which search query or comparison strategy was most responsible. A tool returning booking available is just an observation, not a reward. Reward is the interpretation of that observation in terms of the task objective. Similarly, a judge saying one plan is better than another is not the task itself. It is a signal about trajectory quality. Keeping these distinctions clear prevents a lot of confusion in agent systems. Too little reward information and the agent cannot tell good reasoning from lucky guessing. Too much or too noisy reward, and the agent may chase the wrong objective. Later methods will show how to blend deterministic checks with judge-based signals to build useful feedback. For now, the key point is that reward is the language of improvement. Without it, a trajectory is just a record, not training evidence. These 5 terms all describe records of an agent's behavior, but each one captures a different scope and purpose. Understanding the distinctions between them is essential for later chapters on evaluation, optimization, and memory. A trajectory is more than a transcript or a final answer. It preserves every message, action, tool call, intermediate output, and the final result. Later optimization methods need this path structure because they must know which sequence of decisions was taken, not just whether the end state looked acceptable. A rollout names the full sampled run as a unit of analysis. It may contain one or more trajectories, depending on how the run is segmented. When later sections compare rollouts, they compare full sampled runs. When they inspect trajectories, they look at the detailed behavior inside those runs. Trace carries a stronger connotation of inspectability than learnability. A trace tells you what happened, in order, with inputs and outputs at each stage. A trajectory tells you what happened in a form that can also be used for scoring, ranking, or training. The same record may serve both purposes, but the intended use changes the vocabulary. History is the conversational or operational past available to the system, like prior messages in a chat buffer. Memory is different. It is persisted information intended to influence future sessions, such as a user preference or a note about a recurring task. A trajectory may later be summarized into memory, but memory is the retained information, not the execution record itself. Use this compact key to keep the distinction straight. The trajectory is the flight recorder, the detailed step-by-step record. The rollout is the full sample take used for comparison or optimization. The trace is the inspectable log for debugging. The history is the available past context. The memory is the durable stored information. These terms overlap in practice, but they are not interchangeable, and later chapters rely on these boundaries. This diagram shows how the five terms overlap in a real system. Notice that the trajectory is the innermost detailed record. The rollout wraps the full execution. The trace is the inspectable view. History provides the session context, and memory persists across sessions. Each term names a different scope and purpose, even though the same underlying data may serve multiple roles. A policy is the decision rule that maps context to action. Every optimization method in this chapter works by improving this rule. So getting a clear picture of what a policy is will make everything else easier to follow. The policy does not act on the whole world. It acts on the context the system has assembled so far: the user request, recent messages, tool outputs, and any constraints. For Atlas, that context might include a budget cap and an approval rule. The policy then decides whether to search, compare, ask a clarifying question, or stop. The quality of the policy shows in the quality of those decisions, not just in the final wording. A model can produce a good final itinerary while still having a poor policy if it reached that answer through unreliable or inefficient steps. Conversely, a policy can be strong even when one rollout ends badly due to a noisy environment or a temporary tool failure. This distinction matters in trajectory-based training, where the system may compare candidate runs, assign reward at the rollout level, or compare policies using grouped outcomes. In all those cases, the policy is the object being shaped by evidence. Methods like GRPO and GSPO are best understood as alternative ways to adjust policy behavior when a learning signal comes from group trajectories or relative comparisons. If you hold on to the policy definition as the mapping from context to action, the rest of the chapter becomes much easier to navigate. The methods differ in how they collect evidence, rank behavior, and constrain change, but they all aim at the same target: a better policy for the agent's decision loop. GRPO and GSPO differ in how they collect evidence, rank behavior, and constrain change, but they all aim at the same target: a better policy for the agent's decision loop. Keeping the policy definition as the mapping from context to action makes the rest of the chapter much easier to navigate. An agent can only learn from behavior it has already produced. Unlike supervised learning, where we can hand the model a labeled example directly, an agent's decisions only make sense inside a sequence of actions and outcomes. So the training signal has to come from trajectories the agent generates, not from a pre-existing label. The agent explores a path, that path gets judged, and the judgment becomes the material it learns from. This is how generation feeds into optimization. That means the distribution of the data matters just as much as the labels themselves. If Atlas only ever samples shallow, one-step responses, it will never learn to handle multi-step planning. But if it samples diverse trajectories, including ones that fail in instructive ways, the learner can start to tell robust behavior apart from brittle behavior. The sampled runs are not just examples. They're the medium through which policy quality becomes visible. A high-quality training set for an agent is one that captures its own behavior under varied conditions. That behavior shows exactly where the policy is strong, where it is uncertain, and where it is misguided. This is why relative evaluation shows up so often in modern trajectory optimization. When a task has many plausible outputs, you do not always need a perfect scalar label for every run. It is often enough to compare several sampled trajectories and decide which is better under a rubric. That comparison turns raw generated behavior into a structured learning signal. For Atlas, two candidate travel plans might both be feasible, but one may respect budget and approval constraints more carefully. That better rollout becomes useful not just as a final answer, but as evidence about which decision pattern the policy should prefer in the future. The deeper lesson is that the agent's own behavior becomes a data source. This is different from scraping text from a dataset. The model is not just consuming examples. It is generating the experience that later teaches it. Once you see agent learning that way, the later sections on reward models, judges, ranking objectives, and test time search all make much more sense. They all operate on sample behavior because sample behavior is the raw material from which improvement is carved. The way an agent gathers and uses experience during training defines its learning mode. Two fundamental modes are online reinforcement learning and offline reinforcement learning, and the choice between them has deep consequences for how the system behaves and how safe it is to deploy. In online reinforcement learning, the agent acts in the environment responds, and that brand new interaction is immediately used to update the policy. The defining feature is the freshness of the experience. This is attractive because the policy can adapt quickly to current conditions, current tools, and current failure modes. If Atlas encounters a new booking interface or a policy rule change, online data reflects that shift right away. The cost is operational complexity. The system must safely gather experience while controlling quality and avoiding instability. Offline reinforcement learning takes the opposite approach. The learner works from a static dataset of previously collected trajectories without needing to gather new interaction during the update phase. This makes the process easier to reproduce and often safer to stage because the data is already known and can be audited. For agent systems, offline data might include old conversations, traces of tool usage, or historical rollout logs. The limitation is that the policy must learn from whatever behavior happened to be recorded, which may not cover rare cases or reflect current conditions. The operational difference matters because agent systems are not just statistical learners. They're embedded in tools, users, and policies. Online learning is closer to training with live traffic, which improves realism but increases risk. Offline learning is closer to learning from replayed recordings, which is easier to control but may underrepresent new edge cases. Many production-minded teams favor a stage path. Collect offline traces, evaluate them carefully, and only later consider limited online adaptation. That caution is especially important in agent settings where incorrect actions can have immediate consequences. Alice provides a simple illustration. If the travel agent learns from fresh session traces as users interact with it, that is online learning. If the same agent is updated from a saved corpus of previous travel planning sessions, that is offline learning. The distinction is not cosmetic. It changes what counts as the training set, how quickly behavior can drift, and how much exposure the learner has to current tool responses. For later methods in this chapter, this distinction also shapes what kind of ranking or reward pipeline is feasible. A core design choice in reinforcement learning is whether the policy that collects experience is the same as the policy being improved. This distinction, on policy versus off policy, shapes how data is generated, reused, and trusted. In on-policy learning, the agent uses trajectories generated by its current policy to update that same policy. The behavior and the target are aligned. For a language agent, that means sampling under the current model parameters and using those exact rollouts for training. The advantage is directness. The updates reflect what the agent is actually doing right now. The downside is that every update requires fresh data, which can be expensive. Off-policy learning decouples data collection from policy improvement. The trajectories can come from an older checkpoint, a different agent, or even a human demonstrator. This makes data reuse possible. You can train on historical logs or past rollouts. The trade-off is a distribution mismatch. The data no longer perfectly matches the current policy. That mismatch must be handled carefully or could destabilize learning. For agent developers, this distinction becomes concrete whenever you have a replay buffer, a trajectory archive, or a preference dataset built from older runs. On-policy methods are conceptually simpler because the data is current, but they're not always the most data efficient. Off-policy methods can extract more value from past experience, but they require careful weighting, filtering, or normalization. That matters because agent trajectories are costly to produce and often costly to evaluate. Atlas makes this concrete. If the current travel policy generates candidate itineraries, and those same runs update the model, that is on policy. If a previous version of Atlas generated the itineraries and the current version learns from them, that is off policy. Keeping these terms straight will make later discussions of trajectory ranking and group-based optimization much clearer. You'll always know not just what was sampled, but by whom and under which policy. Reinforcement learning splits into two broad families, depending on whether the agent learns a model of the environment. Understanding this contrast will help you see why some LLM agents rely purely on experience, while others plan ahead using simulations. Model-free reinforcement learning means the agent improves its policy or value function using only the actual rewards it receives from real interactions. It never builds a separate model of how the world works. For LLM agents like Atlas, this is the natural starting point because the system can learn from log trajectories and outcome judgments without needing a hand-built simulator of airline pricing or booking dynamics. Model-based reinforcement learning adds an explicit representation of how the environment behaves. That model can be learned from data or engineered by hand, and the agent uses it to imagine future states before taking action. In agent systems, this often shows up as search, simulation, or planning over possible next steps. The key advantage is that the agent can cheaply evaluate consequences before committing to them, though the quality of planning depends on how accurate the model is. The real difference is where the intelligence resides. A model-free agent relies on direct experience and feedback signals. A model-based agent uses a representation of the world to choose actions more strategically. Many modern LLM systems blur this boundary because the language model itself can act as a rough, predictive model of possible continuations, while external tools provide concrete feedback. For this chapter, just recognize that search-oriented methods sit closer to the model-based side, while pure reward-driven trajectory updates are more model-free in spirit. Atlas gives a concrete example. If it chooses actions based primarily on previous travel planning outcomes and reward signals, it is operating in a model-free regime. If it also simulates alternative itinerary branches, predicts likely booking availability, or uses a learned environment model to rank future possibilities before acting, it is borrowing model-based ideas. The point is not to force every agent into one box, but to understand the design spectrum. Later sections will use that spectrum to position search and optimization methods more precisely. In many agent systems, the environment does not hand back a clean reward number. Instead, we need a separate component, a reward model, a judge model, or an LLM acting as a judge, to inspect the agent's behavior and produce a quality signal. That signal can be a score, a preference ranking, or a verdict based on correctness, usefulness, or policy compliance. The key idea is that this evaluator turns raw trajectories into something the training or ranking pipeline can actually use. These evaluators become especially important when the task is too complex for a simple automatic metric. Take travel planning as an example. A flight itinerary might be technically valid, but still terrible because it is too expensive, inconvenient, or ignores the user's constraints. A judge model can inspect the whole trajectory against a task rubric and produce a much more nuanced signal than a simple yes or no check. That signal may be imperfect, but it is far more informative than just checking whether the final answer looks right. The phrase LLM judge can sound more magical than it really is. The model is not inheriting absolute truth. It is serving as a preference or quality assessor under a specific rubric, with calibration limits and bias risks. That is why later sections emphasize relative evaluation over isolated scoring whenever possible. Comparing two candidate trajectories is usually easier than assigning a perfectly calibrated absolute score. And even then, the judge remains a supporting component, not the source of learning itself. The practical lesson is that agent learning often depends on a layered evaluation stack. The environment produces facts, the reward mechanism transforms those facts into signals, and the judge model provides comparative judgments over complete trajectories. These components become especially relevant once agent behavior grows long and structured. A single text answer is easy to grade, but a branching, tool-using, multi-step trajectory usually is not. Reward models and judges are how that complexity becomes usable learning data. The practical lesson is that agent learning often depends on a layered evaluation stack. The environment produces facts, the reward mechanism transforms those facts into signals, and the judge model provides comparative judgments over complete trajectories. These components become especially relevant once agent behavior grows long and structured. A single text answer is easy to grade, but a branching, tool-using, multi-step trajectory usually is not. Reward models and judges are how that complexity becomes usable learning data. Relative evaluation is the idea that transforms how we train agents. Instead of scoring a single trajectory in isolation, we compare multiple candidates against each other. That shift makes the learning signal much more reliable, and it opens the door to the optimization methods we will explore next. Absolute scoring asks whether a single trajectory meets a target. Relative evaluation asks which of several candidates is better under the same rubric. For agent tasks, that is a more reliable question because all candidates share the same task and context. The evaluator does not need to be perfect. It only needs to distinguish among candidates well enough to guide improvement. For Atlas, relative evaluation could mean comparing two travel planning rollouts that both search for flights and hotels but took different paths. One might have explored more options before settling, while the other might have accepted the first acceptable fare. The judge need not assign an absolute score of 0.87 versus 0.82. It can simply identify that the first rollout better respected the budget and approval policy. That preference becomes a training signal. This is one reason relative evaluation has become so important. It is often easier to tell which answer is better than to tell exactly how good a single answer is. Relative evaluation also aligns naturally with the way agents explore. A stochastic policy can generate multiple candidate rollouts for the same task. Those rollouts become a small comparison set. The system can then learn from the best one, penalize the weaker ones, or use group statistics to stabilize updates. That logic appears again in GRPO, GSPO, and the search-based methods later in this chapter. If you understand relative evaluation now, those methods will feel like variations on a familiar theme rather than new jargon. The broader conceptual point is that ranking trajectories gives the learner structure. A raw reward number can be noisy, but a comparison among candidates often reveals a clearer preference signal. This is especially valuable in agent systems because the cost of being slightly wrong can be hidden until the full execution path is observed. Relative evaluation makes the path visible. It turns a set of sample behaviors into a usable ordering, and that ordering becomes the basis for subsequent optimization. A concrete example helps clarify the difference between a rollout, a trajectory, and the surrounding record. Let's walk through how Atlas, a travel assistant, handles a trip planning request. Atlas starts with a user request for a 2-night trip within a fixed budget, preferring nonstop flights. The initial state holds the request, budget, dates, and stored preferences. The first action might be a flight search tool call. The observation, candidate prices, durations, and routes, updates the agent context, and then it picks the next action, like searching hotels or filtering results. Every step runs inside the same decision loop. When Atlas produces a recommendation, that's just the final visible output. The full trajectory includes messages to the user, tool calls, intermediate summaries, approval requests, and the final booking suggestion. A single sampled execution of the task is a rollout. Within that rollout, there may be one or more recorded trajectories depending on how the system segments the run. If another run of the same request produces a different itinerary because the policy sampled different branches, that's a different rollout with its own trajectory record. Now imagine one rollout chooses the cheapest flight immediately, while another searches more broadly and finds a slightly more expensive but much shorter itinerary that still fits the budget. A judge model might rank the second rollout higher because it better balances user preferences. That ranking encodes a preference over the path the agent took, not just the final text. The better rollout becomes a learning signal, and the policy that generated it is what gets reinforced or imitated. This example shows why the surrounding record matters. A trace of execution helps debug tool failures or poor branch choices. The conversation history helps the agent remember what the user said. Memory may preserve durable preferences for future trips, like a preferred airline. The trajectory captures the full sequence needed for learning. The rollout is the complete sampled run that can be compared with others. The same agent action may appear in all these views, but each serves a different purpose. Keeping these distinctions clear is essential before moving on to ranking methods and trajectory optimization. Several terms in this field get used interchangeably, but they carry distinct meanings. Getting them right prevents design mistakes later. The most frequent mistake is treating rollout and trajectory as synonyms. A rollout is the entire sampled run, often used when comparing multiple candidate runs. A trajectory is the detailed step-by-step record of what the agent did inside that run. The practical test is simple. Ask whether your sentence is about the full run or the recorded path inside it. That distinction matters when methods aggregate or rank multiple runs. Another common confusion is between trace, history, and memory. A trace is the recorded sequence you inspect to understand behavior. History is the prior conversational or operational context available to the system. Memory is persisted information intended to influence future sessions. A trajectory can be stored in history, and parts of it can become memory, but the terms are not interchangeable. This matters because a system can have a detailed trace without any durable memory, or it can remember a user preference without retaining the full trace that revealed it. A third confusion is treating reward as just a final score. In agent systems, reward can be sparse, delayed, intermediate, composite, or judge-based. It can measure progress toward a goal, compliance with constraints, or relative preference among candidates. That flexibility is powerful, but it means the developer must be explicit about what is being rewarded. If the signal is mislabeled, the policy may learn the wrong behavior very efficiently. The vocabulary is therefore not ornamental. It is a guardrail against misdesign. The final guardrail is to remember that sample behavior is the raw material of learning. A single final answer is not enough to describe how an agent behaves under uncertainty. The decision path, the feedback attached to that path, and the comparison among alternative paths are what make later optimization methods possible. Keep that one idea in mind. Agents learn from trajectories, rollouts provide those trajectories, reward and judges score them, and policies change because of what those sampled runs reveal. System-level improvement versus model-level improvement. Why agent improvement is a layered problem. A common mistake in agent engineering is to treat improvement as if it were a single knob labeled better model. In practice, an agent is a layered system in which the policy, the prompt, the tool surface, the routing logic, the memory policy, the evaluation harness, and a surrounding workflow all contribute to what the user experiences. If the Atlas Travel Assistant produces a weak answer, that weakness may live in the model weights, but it may just as plausibly live in the way the system presents context, decides when to search, decides when to stop, or decides which candidate action deserves execution. The important consequence is that performance is not synonymous with model capability. A capable model placed inside a brittle workflow can behave like a novice, while a modest model placed inside a disciplined workflow can appear surprisingly strong. Figure 3.5. An agent's observed behavior is shaped by multiple layers, not just the model weights. Improvement can target the policy itself or the surrounding system. This is easiest to understand if you separate the brain from the nervous system around it. Changing the brain means changing the learned policy itself. Changing the nervous system means changing how information arrives, how choices are staged, how alternatives are compared, and how execution is governed. Both can improve the final result, but they're not the same kind of improvement, and they do not require the same access, the same data, or the same operational risk. For an open model, direct policy updates may be available. For a fixed or closed model, the surrounding system becomes the main leverage point. That distinction matters because many production teams can still make substantial progress without ever touching weights. A helpful analogy is the difference between rewriting a performer's instincts and changing the production around the performer. If you rewrite the instincts, future performances may become better in a general sense, but that requires deep access and careful training. If you redesign the stage, give the performer better cues, add a conductor, and insert rehearsal checkpoints before commitment, the quality of the live performance can rise even if the performer remains exactly the same. Agent systems behave the same way. They're not only learned policies, they are also orchestrated environments in which a policy acts. The book's later methods make this distinction operational, but the core idea belongs here. Better agent behavior can come from better learning, better orchestration, or both. This layered view also changes how you should think about debugging. When the Atlas Travel Assistant recommends a poor itinerary, you should not immediately assume the model failed to reason. It may have reasoned from weak tool output, been routed too early to execution, lacked a comparison step, or been denied the chance to revise after observing a contradiction. The trace is therefore not merely a record of what happened. It is evidence about where the system created leverage and where it wasted it. That is why this chapter moves from generic feedback-driven improvement into methods that inspect and compare trajectories rather than worship a single scalar score. Direct policy improvement when the model is open. When the model is open and its parameters are available, the most direct improvement path is to alter the policy itself. In agent terms, this means that the model's decision-making tendencies are updated so that future trajectories are more likely to produce desirable actions, better tool choices, or more reliable completion behavior. The mechanism may be post-training, preference optimization, reinforcement learning, or some hybrid procedure, but the essential fact is the same. Feedback reaches the weights. That makes learning persistent. A successful update is not just a local fix for one session. It changes the model's future behavior across sessions and deployments. This route is powerful because it can absorb recurring patterns that are painful to encode manually. If Atlas repeatedly fails to compare travel dates correctly or repeatedly forgets to confirm a policy-sensitive booking step, those failures can be turned into training signal. The model can then internalize a better default behavior rather than relying on an ever-growing scaffold of prompts and exceptions. In that sense, policy improvement is the deepest form of correction. The behavior is no longer merely enforced by the system. It is learned by the policy. That advantage is especially important when the same mistake appears across many tasks, because a learned correction can generalize farther than a brittle rule. The limitation is access. If the model is closed, proprietary, or operationally fixed, then the most direct training route is unavailable. Even when access exists, weight updates are not always the right first move. They carry cost, require curated data, risk regression, and can overfit to the exact feedback distribution used during training. A team often discovers that the apparent model problem is actually a workflow problem, and in those cases, training a better policy can be an expensive way to compensate for poor orchestration. Open access creates an option, not a mandate. The point of learning methods in this chapter is not that every failure should become a training run, but that some failures are most efficiently corrected at the policy level. It is also worth separating direct learning from indirect selection. When a model is improved through RL or post-training, the policy itself shifts. By contrast, if you sample several candidate answers and simply choose the best one at runtime, you have improved system output without changing the policy at all. Those two mechanisms can look similar from the user's perspective, but they are fundamentally different. One changes what the model tends to do. The other changes which of its possible behaviors you decide to trust. Later sections build on that difference, because ranking-based methods can blur the line between learning and selection in a useful way. Improving the agent without touching weights. If the model is fixed, the system around it still offers many ways to improve the observed agent. The most obvious lever is prompting, but prompt shaping is only the entry point. The agent can be given better task decomposition, more explicit plan-act-observe structure, cleaner tool descriptions, stronger output constraints, different routing rules, or more appropriate stop conditions. It can be made to ask for approval before sensitive actions, to consult a retrieval tool before answering, or to branch into a compare and select stage instead of acting on the first plausible completion. Each of these changes leaves the model untouched while changing what behavior emerges from the same underlying capability. Tooling is often the highest leverage system-level change. A fixed model can appear weak when it must invent facts, calculate by hand, or reason over stale memory. The same model can appear much stronger when given a search tool, a calculator, a booking API, or a policy lookup function. In that case, the improvement is not the model suddenly becoming smarter in isolation. It is the system reducing the amount of unsupported reasoning the model has to do and replacing it with reliable external operations. For Atlas, this may mean a better search and compare stage for flights, a stricter validation step for dates and budgets, or a handoff to approval before purchase. None of that requires changing weights, yet the user experiences the system as more competent. Routing logic is another frequently underestimated lever. A single model can be routed differently depending on task type, confidence, risk level, or ambiguity. One route may answer directly when the task is simple. Another may trigger retrieval. Another may branch into multiple drafts. And another may interrupt for human review. The model did not improve, but the policy governing when and how it is used did. That distinction becomes especially important in production because many failures are not semantic failures of the model's language ability. They are control flow failures, where the wrong path was chosen too early or too late. A good routing policy can hide the rough edges of a fixed model better than a year of prompt tinkering. Memory policy and evaluation policy also belong in this category. If Atlas remembers a user's preferred departure airport, budget ceiling, or hotel style across sessions, the result can be far more useful than a generic model response, yet the model itself remains unchanged. Likewise, if the system has a better internal evaluator that knows how to score itineraries for feasibility, total cost, and policy compliance, it can choose better candidate actions before committing. The same is true for workflow design. A workflow can enforce intermediate verification, structure comparison, or explicit handoffs so that the model's output is not accepted until it survives a second look. In all these cases, the surrounding system acts as an amplifier, filter, or governor. The practical implication is that closed model systems are not stuck. They are simply constrained to improve through architecture rather than retraining. This is often a feature, not a defect. Many production teams would rather invest in robust orchestration than in risky model updates, especially when they need predictable behavior, stable latency, or compatibility across multiple backends. For that reason, the ability to improve without touching weights is not a second-class strategy. It is a core engineering strategy, and in many products, it is the most cost-effective one. What changes in the observable trajectory? Although model-level and system-level improvement are different in mechanism, both become visible in the trajectory. A trajectory is the sequence of decisions, tool calls, observations, and intermediate outputs that the agent produces while pursuing a task. That sequence is where improvement leaves evidence. If Atlas improves because the policy got better, the trajectory may show fewer useless queries, better decomposition, or cleaner final recommendations. If Atlas improves because the workflow got better, the trajectory may show the same model outputs being guided into more reliable branches, filtered by stronger checks, or supplemented by more useful tools. Either way, the trace changes in ways that can be inspected. This is why the trace is more valuable than the final answer alone. A final answer tells you what was omitted. The trajectory tells you how the answer came to be. It may reveal that the system took a wrong turn early, that it produced a good candidate but failed to retain it, or that it had two strong options and chose the weaker one because the ranking step was absent. Those details are not academic. They identify where the leverage resides. A model update addresses one class of trace patterns. A workflow redesign addresses another. Without the trace, those classes collapse into an undifferentiated notion of bad output. The same trace can therefore diagnose both actor and stage. If the model repeatedly hallucinates unsupported travel constraints, the defect is in the actor. If the model produces reasonable alternatives, but the system never compares them, the defect is in the stage. If the model asks for clarification, but the workflow skips the interrupt, the defect is in orchestration. Good engineering practice depends on not confusing those failure modes. Otherwise, you risk pushing the wrong fix into the wrong layer and paying for it twice. Once in implementation cost, and again in residual error. A subtle but important point is that trajectories are not only useful when they fail. Successful trajectories are equally informative because they show what a good path looks like under the current system constraints. In a travel planning task, a trace may show that the best performing runs always check budget before filtering for airline preference, or that a particular tool call sequence avoids dead ends. Those patterns are useful whether the next improvement happens in the policy, the workflow, or the ranking harness. The trajectory is thus a form of executable evidence. It records behavior in a way that can be mined, compared, and reused. Why trajectories are the reusable evidence layer. The reason trajectories matter so much is that they're the shared substrate between learning and system redesign. If you're changing weights, trajectories become training examples, preference data, or policy gradients. If you're changing the system, trajectories become debugging artifacts, routing evidence, and design input for prompts, tools, or control flow. The same record can serve both purposes because it captures what the agent tried, what it observed, and where execution converged or diverged. That makes trajectories the reusable evidence layer for agent improvement. This reuse matters in practice because agent behavior is often too multi-step to summarize safely with a single label. A trajectory can expose not only whether the final outcome was correct, but why it was correct or incorrect. Did the agent search before committing? Did it ask for approval when policy required it? Did it take a high-cost route when a cheaper route was available? Those are different kinds of evidence. The trace preserves them, which is precisely why later optimization methods can use grouped rollouts instead of single isolated judgments. The model or workflow does not need a perfect theory of the task as long as the evidence of behavior is visible and structured. Trajectories also help create better examples for future improvement. A good run can become a template. A bad run can become a counterexample. A pair of similar runs with different outcomes can reveal the critical decision point where the system should have branched differently. In that sense, trajectories are not just logs. They're the raw material for iterative system design. An experienced team rarely learns from output alone. It learns from the structure of execution. That is especially true in agent systems, where the path taken is often as important as the endpoint. This shared evidence layer is what allows the chapter to move from general feedback-driven improvement to relative ranking. Once the trajectory is visible, the question becomes not merely, was this run good, but how did this run compare with the alternatives? That is a much more practical question for language agents than it may first appear, because the alternatives often reveal behavior that a single scalar score would hide. Absolute scoring is often too brittle for language tasks. A single numeric reward sounds attractive because it appears precise. In many language agent problems, however, absolute scoring is brittle. The task may be open-ended. The output may admit several valid forms, and the notion of partial success may depend on hidden trade-offs such as cost, safety, latency, or policy compliance. If Atlas proposes 3 plausible itineraries, one may be slightly cheaper, another may be more flexible, and a third may be easier to book. Which one deserves a reward of 0.78 instead of 0.81? In many cases, the answer is either unavailable or not very meaningful. A scalar score can hide the real structure of the decision. Figure 3.6. Absolute scores can be brittle for open-ended agent tasks, while relative ranking preserves the structure needed for learning and selection. This is one reason language tasks so often benefit from comparison rather than calibration. It is relatively easy for a human or a judge model to say that one itinerary is better than another on the same criteria. It is much harder to invent an absolute score that captures all the criteria cleanly, remains stable across tasks, and can be interpreted as a meaningful quantity. Absolute rewards also invite false precision. A single number can make a noisy judgment look authoritative. In reality, the judge may only be confident that one rollout is better than another, not that either has any universal numeric worth. Open-ended agent behavior makes the problem even more pronounced because the correct answer is rarely a single string. The quality of a trajectory depends on whether the agent decomposed the problem well, chose sensible tools, recovered from errors, and arrived at a valid plan. A flat score at the end may miss those nuances entirely. If the final answer happens to be acceptable, the system may still be learning from a bad route. If the final answer is imperfect, the system may still have taken the best available path under uncertainty. For training and debugging alike, those distinctions matter. A better way to think about the issue is that language agent tasks often have clearer orderings than they have calibrated measurements. The system may not know how much better one attempt is in absolute terms, but it can often tell which attempt is preferable. That is the opening through which relative ranking becomes so useful. Why groups of trajectories reveal more than one rollout can. A single rollout tells you what happened on one path. A group of rollouts tells you what happened across several plausible paths under the same task and constraints. That difference is enormous. With only one trajectory, you can observe success or failure, but you cannot easily tell whether the outcome was robust, accidental, or dependent on a lucky early choice. With a group, variation becomes visible. You can see which candidate was more systematic, which one was overconfident, which one wasted steps, and which one recovered cleanly from uncertainty. This comparative view is especially valuable in agent tasks because the path to success often matters as much as the final result. Suppose two atlas trajectories both end with a reasonable travel plan. One of them arrived there by asking a clarifying question, checking budget, comparing two routes, and confirming policy. The other arrived there by making a lucky guess that happened to satisfy the constraints. A single score may treat them as equivalent. A group comparison will not. The first trajectory is a more reliable pattern to learn from because its strategy is more repeatable. Group comparison also exposes failure modes that are invisible in isolation. One rollout may fail because it searched too late. Another may fail because it searched too broadly. A third may fail because it ignored a tool result. Taken together, those failures teach you something about the system's decision boundaries. They reveal not just that the agent struggled, but how it struggled. That diagnostic value is why relative methods are so effective in practice. They compress a family of behaviors into a smaller set of contrasts that are easier to reason about than a stream of independent scalar rewards. There's also an operational advantage to groups. They make it easier to separate the best behavior from the noisiest behavior without requiring perfect labels. If one trajectory is clearly superior to the rest, the system can learn from the contrast even when none of the runs is ideal. This is particularly helpful when the task is hard, the judge is imperfect, or the reward is only partially specified. In those settings, learning from which one is better is often far easier than learning from how good is this one on a universal scale. Relative ranking as the bridge from observation to optimization. Relative ranking is the practical bridge between seeing many trajectories and using them to improve behavior. The ranking signal does not need to declare an absolute truth about any one rollout. It only needs to express preference among the rollouts under the same task. That modest requirement is exactly what makes it useful. If the system can identify that one Atlas itinerary is more feasible, more policy compliant, or better balanced than another, it has enough information to guide optimization even when it cannot assign a perfect score. The strength of ranking lies in what it preserves. A numerical score often collapses rich behavior into a single value. A ranking preserves comparison structure. It can tell you which trajectory won, which one lost, and sometimes how the losers differed. That comparison can then feed learning methods that update a policy toward preferred behavior without demanding that the reward function be fully calibrated. In a language agent setting, this is a major practical advantage because task quality is often easier to judge relationally than absolutely. Ranking also creates a natural feedback loop for iterative system design. If a particular workflow consistently produces the best ranked trajectories, that workflow deserves more weight. If a certain routing rule consistently sends the agent into poor branches, that rule deserves revision. If a candidate generation strategy produces diverse but low-quality options, it may need a better proposal stage rather than a better selector. Relative ranking thus supports both learning and engineering. It is not merely a training trick. It is a structured way to understand what kind of improvement is needed. This is the conceptual handoff to the methods later in the chapter. Once a system can compare grouped rollouts, it can begin to optimize against relative preference rather than brittle absolute reward. That is the space in which ranking-driven post-training methods live. The exact algorithm may differ, but the logic is already present here. If the task is easier to compare than to score, then comparison should become part of the learning signal. Atlas Travel Assistant as a concrete branching example. Consider two versions of the Atlas Travel Assistant answering the same bounded planning request. In the first version, Atlas receives the request, produces one answer, and commits. That path is fast and simple, but it leaves little room for correction. If the model underestimates a budget constraint or misses a policy requirement, the mistake becomes the final result. The trajectory is short because the system never made room for alternatives. In production, this kind of direct answer workflow often looks clean until the first ambiguous request arrives, at which point its simplicity becomes a liability. Now consider a branched version of Atlas. The same model first proposes 2 or 3 candidate itineraries or action plans. The system then evaluates them against the same criteria: feasibility, cost, timing, policy compliance, and user preference. After comparison, it selects the strongest candidate and may optionally refine it before presenting it. Nothing about the model had to change for this to happen. The improvement came from the surrounding workflow, creating a space for alternatives, and using ranking to choose among them. From a user's perspective, the result is a better answer. From a system's perspective, the gain came from orchestration. What matters most is not that the branched version always find a perfect plan. It rarely will. What matters is that the system can avoid committing to the first plausible path. That single design choice changes the quality distribution of outcomes. The same base model can look mediocre in a one-shot loop and competent in a compare and select loop because the workflow has exposed a better part of its behavioral range. This is one of the central lessons of the chapter. Realized performance is a product of the model and the system that surrounds it. The Atlas example also shows why group trajectories are so useful for diagnosis. If one candidate fails because it ignores a time constraint, another because it is too expensive, and a third because it violates a booking rule, the system learns more from the comparison than from any single answer. The ranking does not merely tell you which one to keep. It tells you which failure modes matter, which trade-offs are occurring, and which part of the workflow should be improved next. That is the bridge from observed behavior to better policy, better orchestration, or both. The practical takeaway for the rest of the chapter. The central distinction to carry forward is simple but easy to lose under the vocabulary of modern agent training. Model-level improvement changes the policy, while system-level improvement changes the conditions under which the policy acts. In an open model, post-training or RL can alter the learned behavior directly. In a fixed model, prompts, tools, routing, memory, and workflow design can still produce major gains. In both cases, trajectories are the evidence layer that makes improvement possible. The second takeaway is that a group of trajectories is often more useful than a single score. Language agent tasks are frequently easier to compare than to calibrate, and relative ranking is the mechanism that turns that fact into an optimization signal. A group reveals which rollout is best, which is worst, and why the difference exists. That diagnostic value is what makes ranking such an effective bridge from ordinary feedback to the formal methods that follow. Keep that distinction in view as the chapter continues. Some methods will improve the policy itself, some will improve selection among candidate behaviors, and some will improve the surrounding workflow. They are related, but they are not interchangeable. The discipline is in knowing which layer you are changing and what kind of evidence you have for changing it. KL divergence regularization helps keep a model's predictions close to a reference distribution, which is especially useful when training with relative ranking objectives. This combination stabilizes training by preventing the model from assigning extreme probabilities to any single outcome. A policy that improves itself without restraint can become brittle long before it becomes brilliant. That brittleness usually starts as a quiet drift rather than a dramatic failure. A travel planning agent like Atlas might get high rewards for finding cheap fares, then start overemphasizing price at the expense of arrival times or cancellation risk. The policy becomes narrowly specialized around whatever the last round of feedback favored. That is not genuine improvement. It is accidental overfitting. When feedback is noisy or partial, the problem gets worse. A judge might score one itinerary highly for being concise, while penalizing another equally valid one for including a careful caveat. Chasing those local signals too aggressively can make the agent lose useful habits faster than it gains new ones. The figure shows how unconstrained optimization can pull the policy away from its competent baseline. A stability constraint acts like a leash. It still allows movement and adjustment, but prevents a sprint away from prior competence. The point of a stability constraint is not to freeze the policy. It prevents a training run from turning the agent into a different system every time it sees a new reward spike. For Atlas, that means it can learn better itineraries without abruptly forgetting how to ask clarifying questions or stay within approved tools. In iterative self-improvement loops, each generation of candidates drifts toward the last round's accidental winners. Over enough iterations, diversity shrinks, and the agent produces the same style of answer, even when it is not appropriate. Stability constraints slow that collapse, preserve breadth, and keep learning proportional to evidence rather than momentary score variance. KL divergence is the formal mechanism that turns the idea of a leash into an optimization term. It measures how much probability mass the current policy assigns relative to a reference policy, And when the current policy starts to prefer actions the reference considered unlikely, the KL value rises. The new policy is not simply asked to do better on the current batch of data. It is asked to do better without straying too far from the distribution that already encoded useful behavior. The key conceptual move is to treat KL as a soft trust region rather than a hard prohibition. A hard constraint would refuse any update beyond a fixed boundary, which sounds neat but is often too rigid for real agent training. A soft penalty allows the optimizer to move when the reward signal is strong enough, but it makes that movement more expensive as the update departs farther from the baseline. The result is a form of controlled plasticity. The model can still learn that a particular itinerary pattern is superior for a class of prompts, but it must pay a price if that new preference would sharply distort the policy's broader behavior. It is important to distinguish the different policies that appear in the learning loop. The current policy is the one being optimized now. The old policy is the snapshot used to generate the sampled completions or to define the importance ratio for the current update step. The reference policy is the more stable anchor, often a prior checkpoint or a supervised baseline that represents acceptable behavior. These are not interchangeable labels. The old policy is tied to the latest sampling batch, while the reference policy is tied to the broader notion of competence that should not be abandoned. Confusing them makes the objective look simpler than it really is, and it obscures why the KL term stabilizes learning. A geometric intuition helps here. If you imagine a policy as a point in a huge probability space, the KL penalty acts like a restoring force that resists sudden motion away from a trusted region. It does not say the policy must remain identical to the reference distribution. It says that moving far away should be justified by enough reward to compensate for the expected loss of prior behavior. In agent terms, the model is allowed to become more specialized, but it must earn that specialization. The optimization is therefore not merely maximizing reward. It is maximizing reward under a constraint that preserves the shape of the agent's competence. The formal expression is simple, but its effect is operational. The divergence is computed between the current policy and the reference policy over sample completions, and its penalty is added to the learning objective. This formula says the KL divergence from the reference policy to the current policy is the expected log ratio of their probabilities over completions sampled from the current policy. It is not a decorative formula. It is the mathematical statement that the training objective should prefer policies that improve while remaining recognizably close to the one that was already useful. The penalty becomes part of the actual training pressure. So any step that benefits reward but also pushes the model into unfamiliar probability regions must justify that drift explicitly. The model earns its specialization. This is not a decorative formula. It is the mathematical statement that the training objective should prefer policies that improve while remaining recognizably close to the one that was already useful. The penalty becomes part of the actual training pressure. So any step that benefits reward but also pushes the model into unfamiliar probability regions must justify that drift explicitly. The KL penalty does not just add a number to the loss. It changes how the optimizer responds to reward signals, especially when those signals are noisy or uneven. Without a stability term, a few unusually high rewards can dominate a batch update. If one completion happens to look excellent to the judge, the model may quickly raise the probability of the specific token patterns that appeared in that response, even if those patterns are not robust. With KL regularization, that same reward spike is filtered through a preservation cost. The update still leans in the better direction, but cannot swing wildly on the basis of one rewarded sample. This has a direct effect on learning dynamics. Smaller effective steps preserve more of the model's existing skill set, which matters a great deal when the agent is already useful before fine-tuning. In Atlas, the base policy may already know how to compare flights, check constraints, and ask for approval when needed. A weekly regularized update might improve one narrow benchmark but degrade all of those other behaviors. A KL term reduces the chance that the model forgets those common-sense execution habits while chasing a reward metric. The KL weight controls the strength of this leash, and the right weight is a systems decision rather than a purely mathematical one. If the penalty is too strong, the policy learns slowly and may never depart far enough from its initial behavior to capture new reward structure. If the penalty is too weak, the policy becomes eager, brittle, and increasingly sensitive to the noise in the reward channel. This trade-off is especially important in settings where the feedback is sparse or mediated by a judge model. The practical effect is most noticeable when the reward signal is uneven across prompts. Suppose Atlas receives a high score for a travel plan that was concise and executable, but a similar prompt later yields a noisy low score because the judge was conservative about risk language. A large update in response to that low score may erase useful behavior that was not actually the problem. KL regularization reduces this instability by requiring enough consistent evidence before the policy moves materially. It does not eliminate exploration, but it makes exploration more deliberate. There's also a deeper reason the penalty is soft rather than absolute. Agent behavior is not a single scalar to be improved monotonically. It is a multidimensional distribution over responses, tool calls, and intermediate reasoning patterns. A hard boundary would make the optimizer blind to situations where the policy should decisively change in one region while remaining conservative in another. A soft penalty allows some dimensions of the behavior distribution to move more than others, which is exactly what one wants when improving agents. The learning signal in agent training can come from two fundamentally different sources: absolute supervision, where a response is judged against a fixed target, or relative feedback, where responses are compared to each other. Understanding this distinction is key to designing effective training loops for agents that operate in open-ended domains. In traditional supervised learning, the model is trained to match a single correct answer. That works well for tasks like classification or grammar correction, where the target is unambiguous. But many agent tasks, like travel planning, have no single right answer. A valid itinerary might prioritize cost, speed, flexibility, or safety, and different users will value those trade-offs differently. In those cases, asking whether a response is absolutely correct is less useful than asking which of two responses is better for the same prompt. Relative feedback shifts the focus from assigning a perfect absolute rating to comparing candidates. Instead of forcing an evaluator to give a numeric score to one response, the system asks it to rank or distinguish better from worse within a set. Humans are much better at choosing among alternatives than at assigning an ideal score. In judge models, it can also be more stable when comparing siblings produced by the same policy. That is why relative ranking has become such a practical foundation for agent learning. The usefulness of relative feedback grows when correctness is ambiguous, expensive, or only partially observable. A planning agent may not know whether the best travel plan is the one with the lowest fare or the one with the lowest risk of misconnections. A support orchestrator may need to decide whether a cautious escalation is better than a direct answer. In these cases, the evaluator cannot provide a universal absolute label, but it can still say that one candidate is better than another under the stated criteria. Relative ranking exploits a weaker but more obtainable form of supervision, and that can be a better fit for agent tasks than pretending a single gold answer exists. This changes the role of the scorer. It no longer needs to define truth in an absolute sense. It only needs to order or differentiate candidates consistently enough to produce a learning signal. That is why relative ranking pairs so naturally with sampled completions. If the model generates multiple travel plans for the same prompt, the training pipeline can ask which one is more sensible, more complete, or more aligned with constraints. The result is not a claim that the chosen plan is perfect. It is a local preference statement inside a sampled cohort, and that is enough to drive policy improvement when the objective is framed correctly. GRPO and GSPO rely on a simple idea. Take one prompt, generate several candidate completions, and judge them together. This group structure is what makes comparison meaningful. Comparing candidates from the same prompt isolates the policy's choices from differences in the task itself. Atlas might generate one itinerary that prioritizes cost, another that prioritizes speed, and a third that is balanced. If those responses came from different prompts, you'd be mixing task variation with policy quality. Group sampling keeps the ranking signal tied to behavior, not to prompt differences. With only two similar completions, the evaluator learns little more than a weak tiebreaker. More samples reveal a broader range of behaviors, making ranking more informative. But larger groups cost more compute and can introduce noise if the policy is already narrow. Group size is a tunable compromise. This group framing is attractive because it avoids the infrastructure of a classical RL critic. The policy itself produces the candidates, and an evaluator assigns relative scores. For agent systems, that simplicity matters. The pipeline can focus on generating plausible trajectories and ranking them without building a separate prediction head for every intermediate state. A concrete Atlas example makes this clearer. One completion might be cheap, but fragile with tight connections. Another might be more expensive, but operationally safer. A third might be balanced with an explicit approval checkpoint. The group comparison doesn't ask which is globally optimal. It asks which is better under the task's own constraints. That relative structure turns sampled completions into training data. Raw reward scores are not directly usable as a learning signal. Group normalized advantages solve this by comparing each candidate only against its siblings from the same prompt. If we used raw rewards directly, a prompt with unusually large scores would dominate the update, while a prompt with compressed scores would contribute too little. Group normalization expresses each candidate's score relative to its local cohort, not against the universe of all possible answers. The standard construction centers each reward around the group mean and scales it by the group's standard deviation. This turns the group into a local scoreboard. A positive advantage means the candidate outperformed its peers. A negative advantage means it underperformed them. The scaling step is as important as the centering step because it normalizes the update strength across prompts with different score spreads. A group with large raw score spread and a group with tiny spread can now contribute on a comparable scale. That makes training less sensitive to the idiosyncratic difficulty of a specific prompt. There is a variance reduction effect that is easy to miss. The centered and scaled advantage suppresses absolute score magnitude and preserves only ordinal information within the group. That is exactly what relative ranking needs, and it is more robust than trying to calibrate every score as an objective measurement. If every candidate in a group receives nearly the same score, the standard deviation becomes very small and normalization becomes unstable or uninformative. That usually means the sample completions were too similar, the judge was too blunt, or the task was not discriminative enough. Homogeneous groups tell you that either the sampling strategy needs more diversity or the evaluator needs more sensitivity. An LLM does not generate a response in one shot. It builds it token by token, and the way we assign credit during training depends on whether we treat those tokens as separate decisions or as one block. The probability of a full completion factorizes into a product of token-level conditionals. Each token probability depends on the prompt and all the tokens that came before it. This equation says the likelihood of the whole response given the prompt is the product of the probabilities of each token, in order, given the prompt and the earlier tokens. This decomposition is not just notation. It means you can push probability changes directly onto individual token decisions, or treat the whole response as one unit. Those choices lead to different training dynamics. Token-level optimization gives local control. If a risky booking suggestion appears in the middle of an itinerary, you can penalize that specific region. Sequence level treats the whole answer as one unit and distributes the reward across it in aggregate. The same reward can produce different pressure on the model depending on granularity. If the reward cares about the structure of a full plan, a sequence-level signal may align better. If it cares about precise tool use language, token-level signals are more expressive. Credit assignment is the core design choice. Token-level methods spread the pressure across individual tokens. Sequence-level methods evaluate the whole response first and shape the update around the sequence as a unit. GRPO and GSPO sit on opposite sides of this choice. GRPO is a training rule built from 4 pieces: group sampling, reward standardization, token-level relative updating, and a stability constraint. By the end of this part, you will see how these pieces fit together into a single objective. The model first produces several completions for the same prompt. Each completion gets a score, which is then normalized within the group to produce an advantage. The update itself is computed at the token level using importance ratios that compare the current policy to the old one. Finally, the update is clipped and regularized by KL, so it cannot overreact to any single batch. The token level ratio compares how much probability the new policy assigns to each sampled token relative to the old policy. It measures whether the model is becoming more or less likely to reproduce that sampled action at that point in the sequence. When multiplied by a positive advantage, the objective pushes the policy to increase the probability of that token path. A negative advantage pushes in the opposite direction. This gives GRPO a localized learning signal, even though the reward is computed at the sequence level. The clipped objective prevents the optimizer from making updates that are too aggressive in either direction. Clipping is not the same as KL regularization. Clipping limits the per-update ratio, so a single sample cannot produce an outsized policy jump, while KL penalizes overall drift away from the reference policy. The two mechanisms work together. Clipping protects the step size of the current update, and KL protects the global shape of the policy over repeated updates. Here is the full GRPO objective written out. This figure shows the full GRPO pipeline. On the left, multiple completions are sampled from the old policy for a single prompt. Each completion is scored and normalized to produce an advantage. Then, for each token, the ratio of new to old probability is computed and multiplied by the advantage. The update is clipped to stay within a trust region, and a KL penalty keeps the policy from drifting too far from the reference. This is the GRPO loss. The outer expectation is over prompts and groups of completions. Inside, for each completion, the loss averages over tokens. For each token, the ratio W times the advantage A is taken, but clipped to stay within 1 minus epsilon and 1 plus epsilon. The minimum of the clipped and unclipped versions ensures the update is conservative. Finally, a KL divergence term with coefficient beta penalizes the policy for drifting from the reference. The ratio W is defined per token, not per sequence. Here, W for token T in completion, I is the ratio of the probability under the current policy to the probability under the old policy, conditioned on the prompt and all previous tokens in that completion. Read operationally. These equations say that every token in every sampled completion is nudged according to the relative quality of the whole completion, but only within a bounded trust region. The reward is global, the ratio is local, and the stability term is global again. This is why GRPO is attractive for agents. It can learn from sampled trajectories without requiring perfect token-level labels, yet it still preserves enough structure to improve the policy in a controlled way. A practical way to think about it is that GRPO translates reward into token pressure. If Atlas emits a good travel plan, the tokens that made that plan possible become slightly more probable, especially if they were part of a completion that ranked above its peers. If the completion was poor, those same token choices are nudged downward. The policy learns from relative standing within the group, but the update is applied at the token granularity that the language model naturally uses. That makes GRPO especially useful when local wording and local decision points matter. GSBO applies the same relative ranking idea as GRPO, but shifts the optimization target from individual tokens to entire sequences. This matters whenever the reward depends on the completion as a coherent unit. A travel plan is judged as a plan, not as a collection of token decisions. Did the itinerary satisfy constraints? Did it explain trade-offs cleanly? Did it keep the user's preferences intact? Those are sequence-level questions, and GSBO aligns the update with that scale. The sequence-level likelihood ratio is length normalized so that longer responses do not get an unfair advantage purely because they contain more tokens. Here is the quantity that captures that. This expression computes the ratio of the new policy's probability for the whole sequence to the old policy's probability, then takes the geometric mean by raising to the power of 1 over the sequence length. That gives a per token average of the log ratio, which is then exponentiated. Rather than asking whether each token individually became more or less likely, GSBO asks whether the completion as a whole became more or less likely, normalized by length. This ties the update more directly to the quality of the response as an integrated object. The same group normalized advantage can then be reused at the sequence level. The advantage for each sequence is computed by subtracting the mean reward of the group and dividing by the standard deviation, just like in GRPO. This normalizes the rewards so that the update focuses on relative quality within the group. Combining the length normalized sequence ratio and the group normalized advantage gives the GSPO objective. This objective looks just like the GRPO objective, but the ratio S_I is now the length normalized sequence ratio. The clipping keeps the update stable by preventing the ratio from moving too far from 1. The operational consequence is that GSPO pushes the whole answer rather than its individual token fragments. This can be easier to reason about when the evaluator looks at coherence, completeness, or task success across the entire response. It is also more stable for long outputs because the length normalized ratio avoids letting longer completions dominate by accumulating more local token ratios. GSPO is not a weaker version of GRPO. It is a different allocation of learning pressure. The distinction becomes especially relevant for agent-like outputs. A token-level method may be sensitive to each local phrase, which helps if phrasing quality matters. A sequence-level method may be better when the real question is whether the itinerary, taken as a whole, is the right answer. GSPO aligns more naturally with holistic planning tasks, while GRPO offers finer local control when the structure of the output matters at the token level. The core difference between GRPO and GSPO comes down to how they assign credit for the reward. One looks at individual tokens, the other looks at the whole sequence. Understanding this distinction clarifies why you would choose one over the other. GRPO attributes the reward signal back through the sequence more locally, using token-level ratios to shape the policy. That helps the model learn which local choices contributed to a good answer. If a completion succeeded because it chose a better instruction order or a safer wording pattern, GRPO can reinforce those local choices directly. The trade-off is that local credit assignment can introduce more variance, because the update depends on finer-grained probability changes across many tokens. GSPO reduces that granularity and therefore often reduces the number of moving parts in the update. The whole response is judged as a whole, which is attractive when the desired behavior is naturally global. In long outputs, token-level noise can accumulate and make the update sensitive to incidental phrasing. Sequence-level credit assignment dampens that sensitivity by treating the answer as a single object. For planning tasks, that can be a better fit because the important question is not whether a particular token was ideal in isolation. It is whether the resulting plan was the best among the sampled alternatives. The practical consequence is that token-level optimization offers more expressive control, while sequence-level optimization often offers cleaner stability. GRPO can be better when local edit quality matters and when the update needs to distinguish fine differences inside a completion. GSPO can be better when the evaluation is inherently holistic, and the main concern is keeping updates aligned with full response quality. Neither method removes the need for good sampling and good judgment. Both still depend on the quality of the candidate group and the scorer. A useful mental shortcut is to think of GRPO as learning from where in the answer the policy made good or bad decisions, and GSPO as learning from whether the answer as a whole deserves more or less probability. That distinction is subtle but operationally important. The same reward signal can produce very different learning dynamics, depending on whether the optimizer distributes it token by token or sequence by sequence. PPO, DPO, GRPO, and GSPO are often discussed together because they occupy neighboring positions in the same design space, but they do not consume the same kind of supervision. Understanding how they differ in signal, infrastructure, and granularity gives you a practical framework for choosing among them. PPO is the classical policy optimization approach that typically relies on a reward signal and often a critic or value estimate to stabilize updates. DPO shifts toward preference learning and can reduce the need for explicit rollout-based reinforcement machinery. GRPO and GSPO push further into relative ranking training, where grouped samples from the same prompt become the basis for learning signals without requiring the same critic-style infrastructure. A practical way to compare them is by asking three questions. What signal drives the update? What infrastructure is required to produce that signal? And at what granularity is the policy optimized? PPO typically uses reward with additional machinery for variance reduction and control. DPO uses preference pairs and a more direct optimization of preferred versus non-preferred responses. GRPO uses grouped sampled completions and token-level clipped ratios. GSPO uses the same grouped relative signal but applies it at the sequence level. This frame is more useful than memorizing acronyms because it tells you what kind of data and compute each method expects. In agent systems, that distinction becomes a design choice about how much of the learning burden you want to place on the evaluator and how much on the policy itself. A system that can cheaply produce several candidate trajectories and rank them may benefit from GRPO or GSPO-style learning, even if it lacks a richly trained critic. A system with stronger reward model infrastructure might use PPO-like machinery. A system that only has pairwise preference data may lean toward DPO-style training. The common thread is that all of these methods are different ways of turning feedback into policy change, but they differ sharply in where the feedback comes from and how the optimizer consumes it. The family resemblance matters because it prevents a false dichotomy. GRPO and GSPO are not unrelated inventions. They're alternative answers to the same question of how to stabilize and structure policy improvement. They inherit the same concerns about drift, reward noise, and overreaction, and they solve those concerns with a combination of regularization, clipping, and relative comparison. That is why the KL penalty introduced earlier is so central. It is the shared stabilizing idea that makes the more specialized ranking methods viable in practice. The formulas you see here are not abstract decorations. They describe exactly how an agent changes during training. The KL term penalizes movement away from the reference policy. The ratio terms measure updates relative to a previous snapshot. The clipping term prevents any single update from being too aggressive. And the group normalized advantage means learning is driven by relative standing within a sampled cohort, not by an absolute external scale. Together, these pieces define a disciplined update rule for a policy that must keep acting usefully while it learns. This discipline has practical consequences for tuning. A larger KL weight preserves behavior but slows adaptation. A narrower clipping range makes the optimizer more cautious but can blunt learning if the reward signal is strong and consistent. A larger group size usually gives a better relative signal but costs more to sample and score. The best setting depends on how noisy the judge is, how expensive the rollouts are, and how sensitive the agent is to losing prior competence. The same equations also clarify the boundary between training time optimization and later inference time search. Everything here happens during policy improvement, before the agent is deployed, or while a fine-tuning loop is running. The update rules modify what the model is inclined to produce next time. They do not themselves search a tree of alternatives at inference. That distinction matters because one can improve an agent either by changing the policy through learning or by leaving the policy fixed and searching more deeply at test time. The methods here belong to the first category. For Atlas, the underlying lesson is straightforward. If repeated samples show that one travel planning style consistently outperforms another, the policy should be nudged in that direction, but only under a controlled leash. If the winners are judged within a group, the learning signal should be relative rather than absolute. If the plan is better understood as a whole than as a collection of token choices, the sequence-level objective may be the cleaner fit. KL regularization, GRPO, and GSPO are all different answers to the same systems problem. How to let an agent learn from its own sample behavior without letting the learning process destroy the competence that made the agent useful in the first place. For Atlas, the underlying lesson is straightforward. If repeated samples show that one travel planning style consistently outperforms another, the policy should be nudged in that direction, but only under a controlled leash. If the winners are judged within a group, the learning signal should be relative rather than absolute. If the plan is better understood as a whole than as a collection of token choices, the sequence-level objective may be the cleaner fit. KL regularization, GRPO, and GSPO are all different answers to the same systems problem. How to let an agent learn from its own sample behavior without letting the learning process destroy the competence that made the agent useful in the first place. Different reinforcement learning algorithms for aligning language models have different trade-offs. This comparison shows how PPO, DPO, GRPO, and GSPO behave when applied to real training tasks, and what each one prioritizes. The four methods, PPO, DPO, GRPO, and GSPO, are not interchangeable acronyms for better fine-tuning. Each one answers a different control question about how an LLM agent improves, and those differences determine which method is actually usable with the supervision you have. When an agent improves, you need to know what the improvement signal is, where it comes from, how much of the response gets credit for it, and how hard you can push the update before the policy starts to drift. These questions matter more than the optimizer label because they determine whether you can train from scalar rewards, pairwise preferences, grouped relative judgments, or whole sequence rankings, and whether the update stays steady through repeated training rounds. For agent systems, this is not an abstract taxonomy. Useful behavior is often only weakly labeled. An Atlas travel assistant can be told that one itinerary is better than another, or that a completed booking trace is acceptable, but assigning dense, perfectly calibrated reward to each token that contributed to the final plan is much harder. A method that needs a fully reliable critic at every step solves a stricter problem than the data source may support. A method that can learn from relative comparisons among sampled candidates is often more practical, even if it gives up some precision in credit assignment. The crucial engineering question is not which method is theoretically strongest, but which method can extract stable improvement from the supervision you actually have. That is why the comparison axes need to be explicit before any equations appear. One axis is supervision source, scalar reward, pairwise preference, or group relative ranking. Another is dependency structure, whether the method needs a learned critic, a reward model, or only the sampled outputs themselves. A third is optimization granularity. Does the update act token by token, or on the response as a whole? A fourth is the stability mechanism, clipping, KL anchoring, normalization, or some combination of those. Once these axes are visible, the methods stop looking like jargon and start looking like different ways of plumbing the same signal into a policy update. This comparison matrix lays out how PPO, DPO, GRPO, and GSPO differ along those four axes. Look at the supervision source column first. Some methods use scalar reward, others use pairwise preferences, and others use group relative rankings. Then check the require machinery column to see whether each method needs a separate critic or reward model, or only the sampled outputs. The update granularity row shows whether the update acts token by token or on the whole response. Finally, the stabilization strategy column shows how each method keeps the policy from drifting too far. The most important practical distinction is that some methods optimize by estimating how good a single response is in an absolute sense, while others optimize by comparing siblings drawn from the same prompt. Absolute supervision is useful when you can trust the scale of the signal. Relative supervision is useful when the scale is unreliable, but the ordering is still meaningful. For agent training, that distinction is often decisive. A judge may be able to tell which itinerary is safer, more coherent, or less wasteful without being able to say exactly how many reward units separate the two. Group-based optimization turns that limitation into a feature rather than a defect. Before we dive into the equations, it helps to have a clear mental picture of what each method is doing and why they exist. This section gives you that map. PPO is the classic reward-driven approach. It samples behavior, evaluates it with a reward signal, and nudges the policy toward higher expected return while keeping each update small. In practice, PPO usually includes a critic or value estimator to reduce variance and turn sparse rewards into stable advantage estimates. So PPO is not just a policy update rule. It is a small training system built around the policy. DPO takes a different path. Instead of maximizing a reward online, it consumes preference data directly and turns those comparisons into a supervised-style objective. This simplifies the training loop by removing the critic and online rollouts, but it also changes what the model optimizes for preference alignment rather than a learned reward trajectory. GRPO and GSPO are group-relative methods. For a given prompt, they sample multiple responses, compare them to each other, and use that local ranking as the update signal. This replaces an explicit critic with a group-based normalization step. the sample group becomes its own reference frame. A response only needs to be better or worse than its siblings, not good or bad in absolute terms. The difference between GRPO and GSPO is where the optimization happens. GRPO works token by token, using an importance ratio at each position and distributing the group's signal across the sequence. GSPO moves that logic to the sequence level with a length-normalized ratio for the whole response. Token-level updates preserve fine-grained credit assignment. Sequence-level updates align better with tasks judged at the full response level. The cleanest way to keep these methods distinct is to ask what the optimizer can actually see. PPO sees reward through a critic and a policy ratio. DPO sees preferences between outputs. GRPO sees relative group scores applied token by token. GSPO sees the same group scores, but applies them to whole responses with length normalization. The signal source is similar, but the update path is different enough that training behavior can diverge sharply. All four training methods we are about to compare rest on the same foundation: how a language model assigns probability to a response, and how that probability is kept under control during training. When a language model generates a response, it does not produce the whole thing at once. Instead, it picks one token at a time, and the probability of each new token depends on the original prompt and on every token it has already generated. This product formula captures that chain. The probability of the full response given the prompt is the product of the probabilities of each token, given the prompt and all the tokens that came before it. This factorization is not just a notational convenience. It is the bridge that lets a training method decide whether to assign credit at the token level or at the sequence level. Because the response probability decomposes into token probabilities, an optimizer can act on individual tokens directly, or it can combine them into a single score for the whole response. The choice depends on whether the reward is given for the full completion or whether fine-grained corrections are needed. The same factorization also explains why we can compare a new policy against a previous one. A new policy is not trained in isolation. It is measured against a reference or old policy to keep the update from drifting too far. That comparison is often framed as KL divergence. It measures how much the updated policy departs from the reference policy on the responses the new policy now prefers to generate. In practice, the reference policy acts as a guardrail. It gives the optimizer a notion of too far, reducing the chance that a single update sequence pushes the model into a brittle or reward-exploiting regime. Think of this anchoring as a lane marker on a mountain road. The policy may need to move to improve, but it should not veer so far that it loses the competence already encoded in the base model. KL regularization does not prevent movement. It regulates the shape and scale of movement. A common beginner error is to read a KL penalty as a sign that the method is timid. In reality, KL is what makes repeated updates comparable and prevents the optimizer from interpreting transient reward noise as a license to rewrite the model wholesale. The token level and sequence level methods differ in how they use this shared machinery. A token level method sees the sequence as a chain of local decisions, and the update can be computed from token-wise importance ratios. A sequence level method sees the whole response as the object of interest and reduces those local ratios into a single normalized sequence ratio. Both methods depend on the same autoregressive factorization, but they extract different credit structures from it. This is why the autoregressive formula should be understood as more than a probability identity. It is the reason LLM optimization can be phrased as an update over individual token probabilities, yet still be aligned with full response task judgments. Without that factorization, methods like GRPO and GSPO would have no mathematically consistent way to move between local action probabilities and aggregate response quality. KL regularization is often dismissed as just a stability term, but in production agent training, it does much more. Understanding its real roles, bounding policy drift, enabling comparability, and complementing clipping is essential for training agents that learn reliably from noisy signals. The first job of KL is to keep the policy from drifting too far. Without a bound, a single optimization step that exploits a narrow signal can push the model outside the distribution where the reward signal is still meaningful. That is especially dangerous for agents because the model is not just generating text. It is deciding whether to call tools, continue reasoning, or commit to an action. Once the policy distribution drifts, the entire control loop can change in unpredictable ways. The second job is comparability. If two training runs achieve the same reward improvement, but one does so with a small, broadly useful shift and the other overfits to a few narrow tokens, raw reward alone will not tell you which update is healthier. KL gives you a measure of how expensive that improvement was in terms of model movement. That is why KL should be read as part of the update geometry, not as an optional extra penalty. The interaction between KL and clipping is important. Clipping controls the size of the local update when the new policy strays too far from the old one on a sampled example. KL then adds a broader deterrent against cumulative drift across the batch or iteration. These are complementary controls, not redundant ones. Clipping acts like a shock absorber at the level of a single ratio. KL acts like a steering constraint at the level of the overall policy distribution. Together, they make it possible to train on noisy relative signals without the model lurching into instability. A subtle but important point is that a small KL coefficient does not automatically mean a weak training signal. It may mean the opposite. The optimizer is being allowed to learn from sparse or noisy rewards without paying an excessive stability tax. Conversely, a large KL penalty does not necessarily produce a safer policy if the reward signal is badly shaped, because the model may simply oscillate around the reference without learning the intended behavior. The right interpretation is not more KL means more caution, but KL sets the cost of policy movement, and the cost must be calibrated to the quality of the signal. PPO and DPO represent two different philosophies for training language models. Understanding what each requires, what each optimizes, and what each conceals will help you see where newer methods like GRPO and GSPO fit in. PPO is the familiar baseline because it directly addresses the control problem. The policy learns from sampled behavior, guided by advantage estimates, a ratio between old and new policy probabilities, and a clipping rule that prevents overly large updates. In the LLM setting, PPO typically relies on a reward model and often a critic or value model. That critic is not optional decoration. It supplies a baseline that reduces variance and helps distinguish genuine improvement from random reward fluctuations. When a reward signal is sparse or delayed, that baseline can be the difference between convergence and jittering. The strength of PPO is that it is a general-purpose policy optimizer. Its weakness, especially in agentic systems, is that this generality comes with significant operational overhead. You need a reward signal, often carefully designed or learned. You usually need a critic or value estimator, and you have to manage the mismatch between what the critic predicts and what the policy actually experiences during rollout. All of that is feasible, but it makes PPO feel more like a training stack than a single equation. DPO simplifies the picture by moving away from the full online RL loop and into a preference optimization regime. If you have examples of which output is preferred over another, you can directly shape the policy toward the preferred output without separately training a critic to estimate return. This is appealing when the signal is fundamentally comparative. For many practical tasks, humans can say this answer is better, even if they cannot produce a clean scalar reward or per token credit assignment. DPO turns that comparison into a learning rule. The hidden cost of DPO is that it assumes the preference data already captures the behavior you want to encourage. If the preferences are noisy, incomplete, or too narrow, the model learns those preferences faithfully. That could be a feature when the task is cleanly aligned with the preference data, but it can also make DPO less flexible than it first appears. It is direct, but it is only as good as the comparisons it receives. PPO and DPO anchor opposite ends of the reference space. PPO is more machinery-heavy, but explicitly reward-driven. DPO is simpler in the learning loop, but more dependent on the quality and representativeness of preference data. GRPO and GSPO sit between them in a useful way. They keep the relative comparison spirit of preference optimization while preserving a policy update structure that can be used for self-improvement from sampled rollouts. The shift from absolute reward learning to group relative learning is small in concept, but large in practice. Instead of asking whether a response is good in isolation, we compare it to other responses for the same prompt. That local comparison is powerful because ranking is often easier than scoring. For many agent tasks, you don't need a perfect scalar reward for every possible output. You just need to compare a few candidates. For example, given several itineraries, the model only needs to know which one is safer, cheaper, or more coherent under the scoring rule. A reward of 0.7 on one prompt and 0.7 on another may not mean the same thing if the tasks differ in difficulty. But when you generate multiple outputs for the same prompt, the relative ordering among them is far more stable. Normalizing within the group gives a signal that is local to the prompt and less sensitive to global scaling errors. This is why group relative optimization can work without a critic. The group of responses serves as the reference distribution. A response learns from the margin by which it outperforms or falls behind its siblings. That fits agent settings where repeated sampling is cheap, but absolute reward is expensive or noisy. There is also a conceptual advantage for self-improvement. If the policy can sample several candidate responses and compare them, it can bootstrap its own learning signal from the diversity of its outputs. The system does not need an external teacher for every step. It generates alternatives, scores them relative to one another, and uses those rankings as training material. This shifts the burden from exact absolute measurement to relative consistency. GRPO refines policy updates by using group normalized advantages at the token level, replacing the need for a separate critic network. The core idea is straightforward. For each prompt, the policy generates a group of responses. The rewards from those responses are normalized relative to each other, turning absolute scores into a comparative signal. This formula shows the group normalized advantage. Each response's reward is centered by subtracting the group mean, then scaled by the group standard deviation. A response above average gets a positive advantage. Below average gets a negative one. The key insight is that the learning signal is not about absolute reward magnitude. It is about relative performance within the group. This makes the update robust to varying reward scales and focuses on comparative improvement. The update itself uses importance ratios computed per token. These ratios compare the probability of a token under the new policy versus the old policy, determining how much influence that token has on the gradient. This ratio measures how much the new policy's probability for a token has changed relative to the old policy. A ratio greater than 1 means the new policy assigns higher probability. Less than 1 means lower probability. To keep updates stable, the ratio is clipped to a range around 1. This prevents any single token from causing a disproportionately large change in the policy, which is especially important when the advantage signal is noisy. Putting it all together, the GRPO objective averages over the group and over tokens, applies clipping to the importance ratios, and adds a KL divergence term to keep the policy from drifting too far from a reference. This is the full objective. The inner minimum implements clipping, the averages spread the group's signal across all tokens, and the KL term regularizes the update. The structure reveals the design: stable, relative, and group-aware. Each part of the objective plays a role. Clipping prevents large individual updates. Averaging spreads the group signal evenly. The KL term ensures the policy doesn't change too radically. Together, they make GRPO stable and sample efficient. A deliberate design choice is the absence of a critic. Instead of learning a value function, GRPO uses group relative normalization. This removes a moving part from training, simplifying the loop and making it easier to scale when rewards come from judges or heuristics. Token-level updates are a double-edged sword. They can precisely target the tokens that caused an error, which is powerful. But when the reward is based on the whole response, the signal gets diluted across many tokens. For long agent outputs, this mismatch can introduce noise. GRPO's clipping term is often misunderstood. It does not cap rewards. It caps how much the policy can change in response to a sampled advantage. This distinction matters because a noisy advantage can lead to overconfident updates if not controlled. A positive advantage does not automatically justify a large move. If the advantage is noisy, a large update can make the policy chase a fluctuation rather than a real signal. Clipping acts as a safeguard, ensuring the update is proportional to evidence, not intoxicated by it. Without normalization, the scale of the reward group directly influences the gradient. Tightly clustered scores produce weak learning even if the ranking is meaningful, while scattered scores can exaggerate updates. Standardizing within the group makes the signal more uniform across prompts and batches. If the judge is noisy, the group mean may reflect judge idiosyncrasy more than answer quality. If rewards are too close, normalization can inflate tiny accidental differences into seemingly meaningful advantages. Long outputs can also diffuse a sequence-level score across many tokens, rewarding verbosity indirectly. The method is only as informative as the relative signal it receives. A model may become better at producing a few high-scoring fragments while still failing at the overall task. This is especially relevant for agent behavior, where the output is a plan or tool invocation sequence. Token-level updates can blur the boundary between meaningful correction and diffuse optimization. Group relative policy optimization can be applied at the sequence level instead of the token level. That is what GSBO does, and it changes how credit is assigned to the model's output. The group relative advantage structure stays the same, but the unit we optimize changes. Instead of updating per token, we update per complete response. The sequence-level importance ratio is the product of token probabilities raised to the power of 1 over sequence length. That normalizes for length, so longer responses don't dominate the update just because they have more tokens. This looks like a small algebraic rearrangement, but it changes the entire credit assignment. Instead of applying the same grouped advantage to each token separately, we compute a single normalized ratio for the whole response and apply the grouped update once. The advantage is still standardized within the group, same formula as before. The difference is that this advantage is now paired with the response level ratio, not token level ratios. In the objective, the response level ratio multiplies the group's standardized advantage. That is the core of GSBO. The objective averages over the group, taking the clipped minimum for each response. The clipping prevents the ratio from moving too far, just like in PPO, but now at the sequence level. When a judge evaluates whether a booking plan is coherent, safe, and bookable, that judgment applies to the entire response, not individual tokens. Sequence-level optimization aligns with that semantics naturally. GSBO avoids forcing one response-level judgment into many token-level gradients. The model still generates tokens autoregressively, but the update is governed by the aggregate behavior of the full sequence. That reduces overemphasis on superficial local fixes. If a response is good overall, but contains one defective step, GSBO has less direct leverage over that exact token. It moves the policy in the right direction through the aggregate signal, which feels more stable and aligned, but sometimes less precise. Length normalization reshapes the optimization landscape by making scores comparable across outputs of different lengths. Without it, the optimizer can develop a bias toward longer or shorter sequences that has nothing to do with content quality. Length normalization is not a cosmetic detail. Without it, long responses tend to accumulate larger raw importance ratios simply because they multiply many token probabilities together. That creates a structural bias. The optimizer may start rewarding or penalizing length itself rather than content quality. A verbose response can look artificially extreme in ratio space, while a concise response can be underweight even if it is just as good or better. By taking the geometric mean of token ratios through the 1 over O_I exponent, GSBO makes the sequence score more comparable across outputs of different lengths. In effect, the method asks about average per token policy movement rather than total accumulated movement. That is a more principled unit when sequence lengths vary widely, which is common in agent tasks. A short confirmation, a medium-length reasoning step, and a long tool-heavy plan should not be judged on a raw ratio scale that automatically favors one length regime. This normalization also reduces a subtle optimization pathology. The model can otherwise discover that it is easier to manipulate aggregate sequence probability by adding low-information tokens than by improving the actual content. Length normalization makes that trick less attractive. It does not eliminate all length bias, but it narrows the gap between semantic quality and ratio magnitude. The geometric intuition is useful here. Token-level updates accumulate like many small local steps along a path. Sequence-level, normalized updates treat the whole path as a single average displacement. If the road is winding, local steering corrections may be useful. If the destination is judged at the end of the road, the average displacement may be the more meaningful quantity. GSBO chooses the latter interpretation when the task naturally evaluates the whole journey. GRPO and GSBO are two policy optimization methods that handle credit assignment differently. The key difference is whether the learning signal is distributed per token or applied to the whole response. Rather than asking which method is universally better, it is more useful to ask what kind of mistake each one avoids. GRPO gives a detailed gradient signal per token, which helps when local corrections matter. GSBO treats the entire response as the unit of evaluation, which preserves global coherence. This figure contrasts the two approaches. On the left, GRPO spreads the learning signal across individual tokens, so each token gets its own adjustment. On the right, GSBO assigns one signal to the entire response and normalizes by length, treating the sequence as a single decision. In agent training, the choice between these methods often aligns with a task structure. When the output is a multi-step plan, a code patch, or a policy-compliant reply, the quality judgment is typically sequence level, even if the response has internal structure. GSBO aligns more naturally with that kind of reward. But if a single bad token can derail the rest of the completion, GRPO's token-level credit gives the optimizer more precise steering. Stability also differs. Token-level ratio updates treat every token as a separate point of pressure, so the noise grows with sequence length. Sequence-level ratios compress that pressure into one scalar per response, which usually yields smoother training. That compression reduces noise, but it also reduces local credit resolution. A helpful way to frame the trade-off is this. GRPO asks which tokens within the sampled response should be nudged, and by how much. GSBO asks which sampled response should be preferred as a whole, and by how much the policy should move toward it. Those are related questions, but they are not the same. The more your task is judged holistically, the more natural GSBO becomes. The more your task requires local correction, the more you may value GRPO's finer credit assignment. Choosing the right alignment method depends on your reward signal, rollout cost, and evaluation structure. This framework helps you match the method to the problem. PPO gives you a mature policy optimization loop with explicit variance reduction, but that flexibility comes with infrastructure cost. If reward is scarce or rollouts are expensive, the critic and online updates can be heavier than necessary. DPO directly absorbs preference information without building a full rewarding critic loop. But if you need the model to improve from its own sampled outputs over repeated comparisons, DPO is less naturally aligned with that pattern than group relative methods. GRPO works well when the group signal is noisy in absolute terms, but reliable in relative terms. The normalized advantage suppresses scale dependence and makes within group ranking the learning primitive, which is natural for token-level credit assignment. GSBO avoids token-wise overreaction by evaluating whole outputs. Its length-normalized sequence ratio produces more predictable updates when output length varies widely or long completions distort token-level credit. The real choice is about which optimization granularity matches your task judgment unit. Even with a solid understanding of each method, there are several traps that appear again and again during implementation and training. Knowing these pitfalls will help you diagnose problems faster and avoid wasting time on setups that look correct but are fundamentally broken. The most common mistake is to confuse the quality of the supervision signal with the sophistication of the optimizer. If the reward model is inconsistent, the preference dataset is biased, or the judge cannot distinguish important errors from stylistic noise, then both PPO style and group relative methods will faithfully amplify that weakness. The optimizer is not a substitute for task definition. A second mistake is to ignore how reward scale interacts with clipping. Poorly calibrated rewards can make advantage normalization unstable, and clipping may then suppress updates so heavily that training appears flat. Flat learning is not always safe learning. It can mean the optimizer has been constrained so much that useful gradient information never reaches the policy. A third mistake is to overlook sequence length effects. Token-level methods can unintentionally favor verbosity because more tokens mean more opportunities to collect small positive updates. Sequence-level methods can also be biased if normalization is mishandled or the judge implicitly prefers longer responses. Length bias is not solved automatically by switching from GRPO to GSBO. It is a structural issue that must be monitored in the evaluation rule itself. A final mistake is to treat token-level and sequence-level objectives as interchangeable just because they share the same raw reward source. They do not. The same group of sampled responses can produce very different training dynamics, depending on whether the update is distributed across tokens or applied to the full response. That difference is why the choice between GRPO and GSBO is not a cosmetic implementation detail. It determines what the optimizer can notice, how much it can move, and where the learning signal is likely to leak. A comparison table is most useful when it helps you choose, not when it just lists definitions. This part distills the four algorithms into a few stable distinctions that map directly to design decisions you will face. PPO uses a reward signal and a critic to produce token-level updates, with a KL penalty to keep the policy stable. DPO skips the critic entirely and works directly from preferences. GRPO is also critic-free, but uses within-group rankings to compute token-level advantages. GSBO follows the same group-relative logic, but applies it at the sequence level, normalizing by length so the update aligns with full response judgments. The useful way to read that summary is as a signal plumbing map. PPO routes a scalar reward through a critic into policy updates. DPO routes preferences directly into a supervised-like objective. GRPO routes within-group rankings into token-wise updates. GSBO routes the same kind of ranking into sequence-wise updates. Once you see the plumbing, the acronyms stop being a list and become a set of design choices about what kind of information the optimizer can safely trust. For agent training, the central trade-off is always the same: signal quality, update stability, and credit assignment resolution. PPO emphasizes explicit reward optimization and baseline control. DPO emphasizes direct preference alignment. GRPO emphasizes relative self-improvement with fine-grained token credit. GSPO emphasizes relative self-improvement with response-level stability. The method you choose should follow the structure of the supervision you can actually produce, not the prestige of the acronym. ART and ruler are two concrete pipelines that turn relative ranking data into usable preference signals. Each one handles the same core problem, comparing outputs, but they differ in how they collect and structure those comparisons. A single answer is rarely enough to train an agent well, especially when the task has many reasonable paths and the quality depends on how the agent searched, not just what it output. ART solves this by treating multiple trajectories for the same scenario as the basic unit of learning. In a chat interface, every completion looks like a finished artifact, so it's easy to miss the weakness of a single answer. But in an agentic setting, the visible output is only the end of a trajectory. The model may have red context, called tools, revised after a failure, or recover from a bad branch. If you only look at the final response, you throw away most of the behavior that explains why one rollout is better than another. Think of an audition where several performers interpret the same piece. A judge can rank them more reliably by comparing phrasing and timing side by side than by assigning each an absolute score. Relative comparison asks a narrower question. Which trajectory is better in this group, and by how much? That matters because reward signals in agent training are often noisy or expensive. A group gives the judge a local frame of reference that is more stable than a global rubric. The countdown task is a good test because it has a crisp success condition, a valid arithmetic expression using a small set of numbers, but also room for softer preferences like search quality, brevity, and elegance. That means it has a hard feasibility boundary and a softer preference surface. ART and ruler let the system use both at once. Correctness prevents nonsense from being rewarded, while relative ranking teaches the model which valid solutions are better. It's important to keep learning and execution separate. The rollout agent acts during data collection. The judge scores those actions, and the policy update changes future behavior. Conflating these roles is a common mistake. A good rollout can be mistaken for a learned improvement when it's just a sample. ART makes this separation explicit, And that separation is what allows the same pipeline to collect data, rank trajectories, and then train from the ranked results. This diagram shows the three stages of art. On the left, the rollout agent generates trajectories. In the middle, the judge scores them. Notice the comparison arrows indicating relative ranking. On the right, the policy update uses those scores to improve future rollouts. The separation is explicit. Each stage has its own role and feeds into the next. The pipeline is built on four core objects. Understanding what each one represents and how they relate to each other is essential for working with the training loop, debugging, and evaluation. The countdown pipeline starts with a scenario. This is not execution yet. It is a structured description of one task instance, an identifier, a target value, the allowed numbers, and a natural language question. This structure matters because it lets the training loop handle every task consistently while preserving the specific parameters needed for later judgment. The scenario is the source of truth, and everything downstream should remain traceable to it. A rollout is the act of running the agent on a scenario. A trajectory is the record of what happened during that rollout. Rollout emphasizes execution over time. Trajectory emphasizes the collected sequence of messages, choices, tool calls, and metadata. A trace is broader in operational settings, including logging and diagnostics beyond the agent's conversational path. History is narrower, usually referring to the messages the agent can see. These distinctions are deliberate because later chapters rely on them. If they blur together, debugging and evaluation become much harder. A group is the container for multiple trajectories generated from the same scenario. Grouping is the crucial structural move that makes relative evaluation possible. With one rollout per task, you can only ask whether it succeeded. With several rollouts for the same task, you can ask which candidate is most promising, which is superficially fluent but semantically wrong, and which is valid yet inefficient. This extra structure turns a single training case into a local competition, and the judge can score that competition more reliably. The group also lets you compare rewards within a shared context rather than across unrelated tasks where scale and ambiguity differ. The usefulness of grouped rollouts is that they make quality differences visible even when absolute quality is hard to calibrate. One trajectory may solve the task with a direct and legal expression. Another may reach the answer through a longer chain of unnecessary operations. A third may be polished, but invalid because it uses a forbidden number twice. When these trajectories sit side by side, the error modes become legible. That legibility helps not only training, but also debugging. A leaderboard view of a trajectory group reveals whether the model is failing because it is exploring badly, because the judge is rewarding the wrong feature, or because the task itself is underspecified. Art is the scaffold that organizes the entire training process, turning relative ranking into a usable learning system. Its structure determines how tasks are sampled, how rollouts are grouped, and how scores become training signals. Art does not define what good behavior looks like. Instead, it organizes how tasks are sampled, how many rollouts are produced per task, how those rollouts are grouped, how the group is scored, and how the resulting signals feed into a policy update. Without art, ruler-style judging would remain an interesting scoring technique. With it, scores become actionable training data. The loop starts by sampling a batch of scenarios. For each scenario, the agent is rolled out multiple times. Those multiple rollouts are not a luxury. They create the within-group variation that relative ranking depends on. If every rollout were identical, the judge would have nothing to discriminate. If rollouts came from different tasks, the comparison would be contaminated by task difficulty rather than trajectory quality. Art keeps the comparison local by ensuring each group belongs to one scenario. Once rollouts are collected, the judge scores each group. Those scores are not the end of the process. They're used to assign reward-like signals back to the trajectories, sometimes after normalization or fusion with deterministic checks. The policy update is downstream of judgment, and its quality depends on the grouping, judging, and reward shaping that preceded it. Because art has explicit stages, you can stop at any boundary and ask whether the failure happened in rollout generation, judge scoring, reward fusion, or update computation. That is much harder in a monolithic training loop where all those concerns are hidden behind a single opaque loss. Art also lets you introduce guardrails at different points. A deterministic verifier can veto invalid solutions. A judge can rank valid alternatives. A normalization step can keep reward scales bounded. And a held-out evaluator can verify that the model learned something real rather than learning to exploit one judge's quirks. Ruler compares candidate trajectories within a group and assigns relative scores. Instead of asking an LLM judge to produce an absolute score for one trajectory in isolation, it asks the judge to score several trajectories in relation to one another. This shift reduces calibration burden dramatically. Absolute scoring requires the judge to maintain a stable internal rubric across tasks, difficulty levels, and response styles. Relative scoring only requires the judge to distinguish better from worse within a shared scenario. That is a far more local problem, and local problems are easier for models and humans alike. Relative scoring also makes score interpretation more operational. A group of trajectories can be sorted into a leaderboard immediately, which is valuable both as a training signal and as a diagnostic artifact. You do not need to ask whether a raw score of 0.73 means the same thing on every task. You only need to know which trajectory outranked the others and whether the ranking matches human expectations. The poem ranking example makes this concrete. The system prompt and user prompt are shared across three trajectories, and only the assistant response differs. That shared context is the critical precondition for fair relative judgment. If the input context differed, the judge would be comparing different tasks rather than different behaviors. By holding the prompt fixed, the group becomes a controlled comparison set. A practical benefit of Ruler is that it supports debugging as a ranking exercise. When a judge group is sorted by reward and printed as a leaderboard, the differences between trajectories become easy to inspect. You can see which response the judge preferred and ask whether that preference matches your intended rubric. This is particularly useful when the judge model is drifting toward fluency bias, length bias, or overconfidence in style. Absolute scoring asks a judge to assign a number to a trajectory, but many tasks don't have a natural numeric scale. Relative ranking avoids that calibration problem by only asking for local order. When you ask a judge to assign absolute points, it has to solve two problems at once: judging quality and calibrating the scale across tasks that differ wildly in difficulty and structure. Relative ranking removes the calibration burden by only asking which trajectory is better within a small group. Even if a judge's global scale shifts, the training signal stays useful as long as the judge is consistent within each group. Group-wise normalization further reduces sensitivity to score scale, which is why these pipelines remain practical. Think of it geometrically. Absolute scoring tries to place every trajectory on a universal axis, while relative ranking only needs pairwise distances inside a neighborhood. The judge can focus on whether A is more faithful or efficient than B, without solving the harder global problem. If all trajectories in a group are poor, the judge may still rank the least bad one at the top. Flawed rubrics or evaluation artifacts can still lead to misleading preferences. Relative ranking reduces calibration difficulty, but doesn't replace careful task design and monitoring. The countdown task gives us a clear, deterministic way to verify correctness. The goal is not to produce something that sounds reasonable, but an arithmetic expression that evaluates exactly to the target, while respecting the rules about number usage. This makes programmatic validation straightforward. The deterministic judge checks several things: whether the expression is empty, whether it contains illegal characters, whether it uses the provided numbers too many times, and whether the final arithmetic result matches the target. This hard verifier is not optional decoration. It is the structural anchor that prevents the training pipeline from rewarding fluent nonsense. This is where we separate feasibility from preference. A trajectory can be elegant but invalid, or valid but inelegant. The deterministic judge only answers the feasibility question. It doesn't judge cleverness or efficiency. Those softer judgments belong to the learn side of the pipeline. The hard verifier acts like a gate. Unless a trajectory clears correctness, the more subjective reward terms should not rescue it. The countdown judge code shows why this gate matters. It first strips white space and rejects empty or malformed expressions. Then it counts number usage and verifies that no number is reused illegally. Only after those structural checks pass does it evaluate the arithmetic expression and compare the result with the target. The option to enforce integer intermediates is especially important. Some solutions are mathematically valid, but operationally undesirable if they rely on fraction-heavy intermediate states. This kind of verifier gives you a binary signal that is easy to trust and easy to audit. But binary signals are often too sparse to train on alone, especially when the solution space is large. That is why the countdown example does not stop at correctness. It uses correctness as the hard boundary and then layers relative quality judgment on top. This combination is far more informative than either source alone. Hybrid reward fusion is the design that makes the countdown example work. The core rule is that correctness gates everything. If the expression fails the deterministic verifier, the reward stays 0 no matter how polished the explanation sounds. If the expression is correct, a qualitative judge score can then shape the reward further. This preserves the priority of feasibility while still letting the model learn preferences among valid solutions. The basic rule is straightforward. Correctness gates everything. If the expression fails the deterministic verifier, the final reward remains 0 regardless of how polished or human-like the explanation may sound. If the expression is correct, then a qualitative judge score can shape the reward further. This design preserves the semantic priority of feasibility while still letting the model learn preferences among valid solutions. The reward fusion process also normalizes judge scores within each group. That normalization matters because raw scores from a judge may not be comparable across groups. One group might be scored on a narrow range because all candidates are similar, while another might contain a wide spread. If those raw values were used directly, some tasks would contribute disproportionate gradient magnitude merely because their internal score scale was larger. Group-wise normalization maps the judge values into a bounded interval before they are fused with a correctness gate, reducing scale drift and making the reward more uniform across tasks. This diagram shows the fusion pipeline. On the left, the deterministic verifier produces a correctness gate, a binary signal that either passes or blocks the trajectory. On the right, the judge scores for each group are normalized to a bounded interval. The two paths then combine. The correctness gate multiplies with a weighted blend of a baseline term and the normalized judge score. The result is a bounded reward that cannot exceed 1 and cannot survive the correctness filter unless the trajectory has already passed the hard verifier. The combination function in the code makes this logic explicit. It reads the raw reward attached to each trajectory, computes the minimum and maximum within the group, and rescales each trajectory's judge score by the span. It then reads the correctness metric, converts it into a binary gate, and multiplies that gate by a weighted blend of a baseline term and the normalized judge score. The result is a bounded reward that cannot exceed 1 and cannot survive the correctness filter unless the trajectory has already passed the hard verifier. That structure prevents a subtle but common failure mode. A trajectory that is stylistically good but invalid should never outrank a valid solution simply because the judge liked its presentation. The design also admits a helpful mental model. Think of the deterministic verifier as a feasibility filter and the judge score as a soft preference layer. The filter says whether the proposal is admissible at all. The preference layer chooses among admissible proposals. This separation mirrors many production systems where policy enforcement and optimization are distinct concerns. In a booking agent, for example, a reservation tool may refuse an invalid booking before any subjective ranking matters. The countdown task is simpler, but the same architectural logic applies. Hard correctness establishes the admissible set, and relative quality then shapes how the model explores within that set. A practical caution is that hybrid reward can be gamed if the judge overvalues surface traits that are correlated with correctness in the training set, but not in general. That is why the correctness gate is indispensable, but it is not sufficient by itself. If the judge begins to reward overly terse expressions that happen to be valid on the training distribution, the model may learn brittle shortcuts. If the reward scale is poorly normalized, small judge differences may be exaggerated into large training differences. Hybrid reward is therefore best treated as a controlled engineering compromise, not as a philosophical claim that correctness and preference are identical. They are separate signals, and the training loop should preserve that separation. The rollout function is where the abstract training idea becomes an actual agentic execution. It initializes a scenario-specific context, sets up a trajectory object, configures tools, and invokes a React-style agent that can inspect the countdown context, search for solutions, and return a final answer. This matters because the trajectory being trained is not a bare text completion policy. It is a control loop that can call tools, accumulate intermediate state, and then commit to a final expression. The learning signal therefore reflects behavior across the whole execution path, not just the last token sequence. The rollout function is where the abstract training idea becomes an actual agentic execution. It does not simply ask the model for one completion and stop. It initializes scenario-specific context, sets up a trajectory object, configures tools, and invokes a React-style agent that can inspect the countdown context, search for solutions, and return a final answer. This matters because the trajectory being trained is not a bare text completion policy. It is a control loop that can call tools, accumulate intermediate state, and then commit to a final expression. The learning signal therefore reflects behavior across the whole execution path, not just the last token sequence. The tool list is intentionally small, which makes the rollout easier to reason about. One tool reads the countdown context, another searches for a candidate expression, and a final tool records the answer. That separation is pedagogically valuable because it mirrors the distinction between observation, deliberation, and commitment. The agent first confirms the task input, then searches, then returns the proposed expression verbatim. The final tool is especially important because it constrains the shape of the output and gives the pipeline a clear place to capture the answer for downstream judging. In agent training, output capture is not a minor implementation detail. It is the boundary between exploration and scored completion. The rollout also records metadata and metrics as it runs. The trajectory stores the scenario identifier, the target, and the allowed numbers, along with the final correctness value and the arithmetic result if one is available. These fields are not just bookkeeping. They are what make debugging and evaluation possible later. If a trajectory fails, you want to know whether it failed because the agent searched badly, because it used an illegal number, or because the final answer was absent. Metadata is how you preserve that diagnostic surface without overloading the agent's own message history. The point of the rollout function is therefore broader than run the model and collect an answer. It is to package the execution in a form that can be judged, ranked, trained, inspected, and replayed. In that sense, the rollout is the bridge between behavior and supervision. It is the place where the agent's internal search becomes an object that can be scored externally. Art depends on that packaging because the later group-wise steps assume every candidate trajectory is comparable, traceable, and attached to the same scenario schema. The real power of art comes from running multiple rollouts for the same scenario and scoring them together as a group. This section shows why that matters and how it works in practice. Collecting more than one rollout for the same scenario is where art gains most of its leverage. The training loop repeats the rollout function several times per task, wrapping each result into a trajectory group. Think of it as asking several contestants to solve the same problem under the same rules. Those repeated rollouts create a local distribution of behaviors, and that distribution is exactly what the relative judge can exploit. Without the group, you only have a single noisy sample. With the group, you have a comparison set. An important detail is the asynchronous gather step. Agent rollouts may involve tool calls, retries, and variable latency. So grouping does not require candidates to finish in lockstep. It only requires that results be collected into a shared container once they are available. This makes the pipeline scalable enough to handle multiple candidate trajectories per scenario without serializing all execution. The same pattern is useful well beyond the countdown task, because any agentic training setup that samples multiple candidates will face the same need to coordinate asynchronous results before judging them. Once the group is assembled, Ruler can score in one pass. That group-wise scoring is more than a convenience. It ensures the judge sees the candidates in their natural competition set, where the differences are most meaningful. If the judge were called independently on each trajectory, it would need to reconstruct the comparison context internally. By presenting the group explicitly, art removes that ambiguity. The scored group can then be preserved as a training artifact, which is useful for later analysis and for debugging cases where the model learns unexpectedly. The fallback behavior in the source is worth noting because practical pipelines must handle scoring failures gracefully. If Ruler cannot score a group, the original group is preserved rather than discarded. That choice prevents the training loop from collapsing simply because one judge call failed. In production-like systems, this sort of resilience is essential. A brittle pipeline that aborts on every scoring exception is hard to operate, and a training loop that silently drops failed examples can create hidden distribution shifts. Preserving the original group keeps the failure visible and avoids turning an infrastructure problem into a biased training signal. The countdown example shows how a complete training pipeline works from start to finish. Each piece has a specific job, and the way they fit together is what makes the system learn effectively. The pipeline starts with a typed scenario schema. A scenario object stores the target, the allowed numbers, a human-readable question, and a unique identifier. This schema is not decorative. It makes the rest of the pipeline deterministic and inspectable. The conversion function maps raw dataset rows into this typed form, creating separate train and test scenario collections. That split matters because the point of the chapter is to show that the same training recipe can improve performance without contaminating evaluation. The rollout function takes a countdown scenario, initializes a trajectory object, and configures the agent prompt. The system prompt is unusually explicit because the task demands constrained behavior. It states the target, lists the allowed numbers, names the available tools, and describes the process the agent should follow. That explicitness is a training aid as well as a control aid. It gives the model enough structure to search productively while still leaving room for varied trajectories. The use of a React-style agent is appropriate here because the task benefits from interleaved reasoning and action, even if the final deliverable is only an expression string. After the agent is invoked, the rollout checks whether a final answer was actually produced. If so, the deterministic judge validates the expression and writes the resulting correctness signal into the trajectory. That correctness signal is the first reward-bearing artifact. The code also attaches a rubric describing what higher quality solutions should look like, such as using fewer operations and avoiding redundant tricks. That rubric is not directly the reward itself, but it documents the preference surface that the later judge-based score is intended to reflect. In effect, the rubric tells the system what kinds of valid solutions should be preferred without pretending those preferences are as objective as arithmetic correctness. The next phase is group scoring and reward fusion. The training loop produces multiple rollouts per scenario, gathers them into groups, and then applies ruler. The judge groups are passed through the hybrid reward combiner, which enforces the correctness gate and normalizes the relative scores. At that point, the trajectories are ready for training. What the model learns from this sequence is not simply solve countdown. It learns which rollout behaviors are rewarded under a combined regime of hard validity and soft preference, which is a richer signal than an isolated success label. The final test phase reuses the same deterministic judge on held-out scenarios. That reuse is important because it keeps the measurement rule aligned with the training rule. If the model improves on the test set under the same verifier, the improvement is interpretable. You're not measuring a different notion of success from the one used during training. The evaluation, therefore, serves as an apples-to-apples check on whether the learned behavior generalizes to unseen tasks. It does not validate the judge itself. It validates the agent's performance under a fixed task definition. The policy update consumes hybrid scored groups, not raw transcripts. That distinction changes what the model actually learns. The model is not simply imitating a reference answer. Instead, it is optimized over trajectories that were generated, judged, normalized, and filtered through a correctness gate. So the update carries information about both what worked and how well it worked relative to alternatives. In supervised fine-tuning, a single target answer is treated as the desired endpoint. Here, the training signal comes from grouped behavior and relative quality. That makes the update more robust to one-off variability in surface form, because multiple valid trajectories can all contribute if they are admissible and judged favorably. It also means the policy can improve even when no single perfect answer is available, as long as the task supplies a reliable verifier and a usable preference signal. Over many updates, the model is nudged toward trajectories that are not merely correct, but correct in a way the judge finds preferable. That can encourage more efficient search, cleaner final answers, and better tool use. But the supervision is only as good as the reward design. If the judge rewards the wrong style, the model learns that style. If normalization is unstable, the model may chase artifacts of score scaling rather than genuine quality. This legibility is especially valuable in agent systems because failures are often distributed across planning, tool use, and output formatting. A black box update makes it hard to know which part of the behavior changed. A structured art loop gives you enough hooks to diagnose whether the model is getting better at search, better at obeying constraints, or merely better at satisfying the judge. A held-out test set keeps evaluation honest. The same rollout function and the same deterministic judge are applied to unseen scenarios, so any change in performance is directly comparable. The simplicity of the test loop is deliberate. By keeping the evaluation procedure identical to the training task, any drop in performance after a training change is a clear signal, not an artifact of a different metric or scoring style. This apples-to-apples comparison is essential for relative ranking. Several failure modes need attention. Judge noise is the most obvious. An LLM judge can drift toward irrelevant features like verbosity or confidence. Reward hacking happens when a model exploits superficial cues the judge likes. Leakage occurs when evaluation artifacts influence training, breaking the holdout guarantee. And brittle reward scaling can let a few groups dominate updates while others contribute nothing. The safest way to interpret ruler is as a fallible comparator. The deterministic verifier defines what counts as a valid solution. The judge orders those solutions, and the training loop converts those judgments into policy updates. The system stays healthy only when these roles stay separate. Tighten the rubric when the judge is noisy. Revisit normalization when scaling drifts, and check for leakage when evaluation and training look too similar. Art and ruler are best understood as practical infrastructure, not a single algorithmic trick. They make relative ranking concrete, let deterministic correctness constrain the search space, and turn multiple candidate behaviors into a trainable signal. The key leap for agent builders is that the model is no longer just answering, it is competing, being judged, and improving under a controlled, auditable pipeline. Code walkthrough. The shared prompt used for comparison is minimal but conceptually important because it fixes the input context for all candidates. Read the structure first, then trace how each line carries the idea forward. 3 trajectories are then created under that same context so that the judge can compare outputs rather than tasks. Read the structure first, then trace how each line carries the idea forward. Those candidates are bundled into a trajectory group and passed to the relative judge. Read the structure first, then trace how each line carries the idea forward. Once scores exist, they can be operationalized as a simple leaderboard for inspection. Read the structure first, then trace how each line carries the idea forward. The countdown verifier illustrates the deterministic side of the reward design. It enforces syntax, legal number usage, and exact arithmetic evaluation. Read the structure first, then trace how each line carries the idea forward. The scenario schema turns raw rows into explicit training and test tasks. Read the structure first, then trace how each line carries the idea forward. The rollout function converts a scenario into a tool using agent execution and attaches reward metadata to the resulting trajectory. Read the structure first, then trace how each line carries the idea forward. Ruler can then be applied to each judge group, with a fallback to the original group if scoring fails. Read the structure first, then trace how each line carries the idea forward. The hybrid combiner shows the central reward fusion logic. Correct trajectories receive normalized relative quality, while incorrect ones remain zeroed out. Read the structure first, then trace how each line carries the idea forward. The art training loop then iterates over scenarios, collects multiple rollouts per group, gathers them asynchronously, and updates the model with the hybrid score trajectories. Read the structure first, then trace how each line carries the idea forward. The test loop closes the feedback cycle by evaluating held-out scenarios with the same deterministic judge. Read the structure first, then trace how each line carries the idea forward. Test time compute is a separate budget for improving an agent's output without changing its weights or training it further. is a different lever from scaling the model itself. The model weights stay the same, the parameter count does not grow, and no training run happens. Instead, the system spends more inference budget on the answer it is already trying to produce through repeated sampling, refinement, scoring, or tree search. The model is not becoming intrinsically smarter. It is being given more scratch paper to work through the problem before committing to an output. Many production constraints are not about raw model capability alone. A travel assistant can often produce a satisfactory first draft in one pass, but the first draft is rarely the best answer when the task is ambiguous, multi-step, or full of trade-offs. Test time compute gives the system a way to spend more effort on comparing candidates without retraining the model to do the comparison better. The cleanest way to separate this from training time learning is to ask what changes when quality improves. In training, the policy itself changes because optimization updates the parameters. In test time search, the policy stays fixed, but the system changes how it uses the policy's outputs, generating more candidates, scoring them, or searching through a tree of partial answers. The improvement comes from compute allocation, not from weight updates. Imagine two solvers facing the same puzzle. One has a larger brain, the other has the same brain, but more time, more paper, and permission to cross out bad attempts. The first changes the quality of the underlying function approximator. The second changes the quality of the decision process around it. If the model lacks a concept, training is the right lever. If it knows enough but commits too early, test time search can yield a large gain at lower organizational cost. Repeated sampling and sequential refinement are two simple test time strategies that can improve model outputs, but each has a ceiling. Understanding where they help and where they stop is essential before moving to structured search. The simplest form of test time search is repeated sampling. Ask the same model for several independent completions and pick the best one. This is a breadth-oriented strategy. It works when the answer space is wide and the first attempt is just one draw from a distribution of plausible responses. In an agent like Atlas, that might mean generating several candidate travel plans and comparing them on cost, duration, and convenience before presenting one to the user. Repeated sampling works well when a model's internal distribution already contains good answers, but the decoding process lands unevenly on them. The reason is statistical. If good solutions appear with moderate probability, more draws increase the chance of seeing one. That is why it often feels like a cheap improvement. It converts one fragile path into a small candidate set. But there's a hard ceiling. If the model never places a reasonable solution in its support, or if the task requires multi-step consistency that a single independent sample cannot coordinate, then breadth alone will not rescue the output. You may get several different wrong answers instead of one right one. Sequential refinement is the complementary depth-oriented strategy. Instead of creating many independent candidates, the system takes one candidate and improves in place. This matches how humans often work when writing or planning. The first draft is not the product, it is the substrate for correction. In Atlas, a rough itinerary can be revised by removing awkward connections, tightening the schedule, or adjusting around a preferred arrival time. Sequential refinement is especially helpful when the model can critique its own output or use a judge signal to identify where the candidate is weak. Yet refinement alone is also limited. It can become trapped in a local basin where each revision makes the answer more polished, but not more correct. In planning tasks, the model may overcommit to an early structure and keep refining details around flawed foundation. In code or reasoning tasks, it may elaborate a mistaken assumption instead of stepping back and exploring an alternative branch. At this point, ad hoc reruns stop being enough. The system needs a control policy that can decide whether to deepen the current branch or create a new one. That is the role of structured search. Monte Carlo tree search gives us a structured way to explore possible answers. Its four-phase loop, selection, expansion, evaluation, and backup, lets the system decide where to focus search effort, even when the final answer is unknown. The core idea isn't specific to language models. It's a general method for allocating search effort across a tree of possible states. In the LLM setting, each node represents a partial or complete candidate answer, plan, or reasoning state. The tree grows as the system proposes continuations, evaluates them, and uses the resulting scores to decide where to spend more effort. The standard loop has four conceptual phases. Selection walks from the root toward a promising leaf using a node scoring rule. Expansion creates new child states. Evaluation assigns a value or reward, and backup propagates that score upward so parent nodes accumulate evidence about which branches are promising. This diagram shows the 4 phases in action. Start at the root node, then follow the selection path down to a leaf. From there, expand by adding child nodes, evaluate the new node's quality, and then back up that score to update the ancestors. The arrows show how information flows: downward during selection and expansion, upward during backup. For agent design, this structure is valuable because it turns a monolithic answer generation problem into a sequence of local decisions. Instead of treating the model as if it had to know the full final answer in one pass, MCTS lets the system ask a smaller question at each step. Which partial branch deserves more attention? That shift is important in tasks with hidden uncertainty. Atlas doesn't need to know the entire trip plan before search begins. It only needs to know enough to extend a partial route into a more informed one. The tree embodies that progressive commitment. Each node is a provisional answer, and each edge is a controlled bet that the next step will increase quality. The practical version of MCDS in LLM systems is usually less formal than textbook game tree search. There's rarely a perfect simulator of the environment, and the rollout may consist of another model completion or a refinement step rather than a fully autonomous simulation. Even so, the logic remains the same. Search uses a reward estimate to rank partial outputs, then uses repeated sampling to reduce uncertainty about those estimates. The backup stage makes the process cumulative. A child's score should influence its ancestors, because good descendants are evidence that the branch as a whole is worth exploring further. This is also where the distinction between trace and trajectory becomes relevant. A trace is merely the record of what happened. A trajectory is a sequence of states and actions that can be scored as a path through the search space. MCDS operates on trajectories, not just logs. The search tree is not a passive transcript. It's an optimization structure in which the system deliberately selects, expands, and revises branches. That distinction will matter when the same idea is reused later for workflow-level learning, because the object being optimized is not just a single answer, but a controllable sequence of decisions. The UCD formula is the selection rule that makes MCTS work. It balances what the tree already knows against what it still needs to discover. The score has two parts. The first part is the node's average reward so far. The second part is an exploration bonus that grows when the parent has been visited many times but the child has not. This diagram shows how the two terms work together. The value term pulls selection toward branches with high average reward, while the exploration term keeps the search from ignoring branches that have only been tried a few times. Here is the formula. V of S is the node's average value. The square root term is the exploration bonus, the log of the parent's visit count divided by the child's visit count. The constant C controls how much weight the exploration gets. In an LLM search, V of S is typically the average reward of all samples that pass through this node. A high value tells the search that this branch has been fruitful, so exploiting it further is a sensible choice. Think of each child branch as a road. Some roads are well-traveled and known to lead to good places. Others have only been checked once or twice. UCT says, don't drive the same obvious road forever, but don't wander blindly into every unfamiliar street either. The parent visit count N of P grows as the search spends time in that region. The child visit count N of S tells how much direct evidence we have about that node. When the parent is well explored but the child is not, the exploration term rises, making the child more attractive precisely because it hasn't been fully tested yet. Two implementation details matter. First, unvisited nodes return infinity, which forces the search to try them before any visited node. Second, the root node is excluded from UCT because it has no parent, so the logarithmic term would be undefined. These edge cases are exactly where an elegant algorithm can break in practice. This Python function implements UCT. It first guards against the root node and unvisited nodes. Then it computes the average reward and the exploration term using the parent and child visit counts. The exploration weight parameter lets you tune how aggressively the search explores. TreeQuest turns the search loop into three clear operations: generate a candidate, score it, and refine it. This structure makes the search process easier to read and reason about. The initial generation function creates a first candidate and immediately scores it, turning a raw model completion into a searchable state. The candidate is seeded from a prompt and passed through the evaluator, so the search tree has a value estimate from the beginning. One subtle point is that the illustrative code appears to invoke the generation function twice in the return path, which looks redundant. That quirk is common in explanatory snippets to preserve conceptual structure, even when the code is not fully optimized. This function takes a prompt, gets a response from a model, and then evaluates that response to produce a score. The key idea is that the return state object bundles both the answer and its score together, so the search tree immediately has a value estimate for this node. Once the tree has a root candidate, refinement becomes the next local operation. The refinement function does not invent a new problem. It takes the current answer as input and asks for a better version of the same answer. This makes the branch continuation explicit. The existing answer becomes the prompt substrate, and the model is pushed to improve informativeness, accuracy, or clarity. The refinement function takes the current answer and its score, then asks the model to improve it. The prompt explicitly tells the model to be more informative, accurate, and clear. The refined answer is then evaluated again, and a new state is returned. This becomes a child node in the tree. The tree quest pattern is powerful because it transforms generate, judge, and refine into tree operations rather than isolated calls. A generated answer is not just an output. It is a node with a score. A refined answer is not just a rewrite. It is a child state that inherits context from its parent, but can diverge if the new formulation improves quality. The score attached to each node allows the search policy to compare branches that differ in depth, breadth, or style. That comparison is what makes the system search rather than merely iterate. For Atlas, The same pattern supports planning under uncertainty. Suppose the first candidate itinerary is acceptable but not ideal. The system can refine the branch by changing the departure day, adjusting the hotel location, or simplifying a transfer path, then score the revised proposal against the original. If the score improves, the branch becomes more attractive. If not, the system can back off and explore a different branch. That is the practical value of tree search in an agent. It gives the model a disciplined way to say, this idea is promising enough to continue, but not so promising that alternative ideas should be ignored. Search only works when the score is trustworthy enough to guide traversal. When the evaluator is itself a language model, the system generates candidates and judges them with a structured rubric. That arrangement is powerful for tasks without external ground truth, but it is also fragile if the judge's output is hard to parse into a numeric signal. The evaluation function asks the model to return JSON and then parses the result into a typed score. That structured output is what makes the score usable as a control signal for tree search. Structure parsing is a defensive measure. If the judge returns a sentence instead of a score, the parser cannot extract a clean numeric input. The fallback score is a recovery path, not a statement of truth. It assigns a neutral value, so the search continues rather than breaking entirely. The function builds a prompt that asks the model to return a JSON object with a score key. It then uses the parse method with a response format to enforce structured output. If anything goes wrong, a malformed response, a network error, the exception handler returns a neutral 0.5, keeping the search loop alive. If the judge is too lenient, mediocre branches get overvalued. If it is too strict, promising but unconventional candidates get suppressed. In agent systems, candidate outputs are often close, so the judge's ranking power matters more than absolute calibration. The search needs a scoring function that is more stable than random noise. Think of the judge as an audition panel rather than a source of truth. The panel can still be wrong, biased, or distracted. The moment the search algorithm assumes the judge is infallible, it becomes vulnerable to reward hacking, brittle parsing, and evaluation drift. Adaptive branching means the algorithm decides, at each step, whether to explore a new possibility or refine an existing one. This choice is driven by the current state of the search, not a fixed rule. Early in a difficult task, the system knows too little to justify heavy refinement, so it spreads out and samples alternatives. Later, once one branch looks promising, it invests more depth in improving that branch. If uncertainty is high, new lanes reveal whether the current route is a dead end. If one route already shows promise, deeper refinement increases the quality of a near solution instead of wasting compute on unrelated paths. The code-level loop makes this concrete. The search begins with an initialized tree, then repeatedly applies a step function that can either expand or refine according to the ABM-CTS policy. At inspection points, it queries the tree for the current top candidate and prints the best so far answer. This turns search into a live decision process where you can surface an acceptable answer before exhausting the budget. The loop runs for a fixed number of steps. Each step calls the algorithm's step function, passing the current tree in a dictionary with the LLM refinement function. Every 5 steps, it inspects the tree using top_k to get the best candidate so far and prints its answer and score. After the loop, it retrieves the final best answer. Naive repeated sampling treats each candidate as an independent draw and leaves selection to the end. ABM-CTS uses the tree structure to make selection continuous. It learns from earlier branches, biases later exploration, and lets the search policy move between exploration and exploitation as evidence accumulates. The ABM-CTS family has several variants, but the goal is to understand the design space rather than memorize every symbol. The practical objective remains the same. Spend more compute where the evidence says the next increment is likely to help. One variant uses a Bayesian score to maintain posterior beliefs about which branch deserves more expansion. Another distinguishes generation nodes from continuation nodes, encoding whether the next action should open a new candidate or extend an existing one. The details differ, but the practical objective stays the same. Instead of asking only which branch has the highest average reward, a Bayesian variant asks which branch has the best combination of expected value and uncertainty. A branch with uncertain but potentially high reward should not be treated the same as a branch whose high score is already well established. This distinction helps encode that not every step in agent reasoning has the same purpose. Some steps are exploratory, some are corrective, and some are consolidating. ABM-CDS uses that structure to avoid flattening all search into the same kind of step, making it a better fit for LLM workflows. The main implementation lesson is to keep the mental model simple even when the variants are not. Understand that the algorithm chooses between widening the tree and deepening a branch, that the choice depends on current uncertainty and value estimates, and that the top-ranked state can be inspected at any point. Once that model is in place, the variants become design options rather than conceptual obstacles. Test-time search is not free. Every extra branch, judge call, or refinement step costs latency and compute. In production systems, the trade-off between answer quality and response time is the central constraint. For an interactive system like a travel planner, a deeper search might produce a better itinerary. But if the judge and refinement loop add too much delay, the user experience degrades. The gain may not be worth the expense. A high branching factor increases the chance of seeing a useful alternative, but it also multiplies the number of candidates that must be scored. If the judge is expensive, broad search becomes cost-prohibitive quickly. If the judge is cheap but noisy, a wide tree can magnify scoring errors. Search procedures can accidentally regenerate near-identical candidates, especially when prompts are similar or temperature is low. Redundant branches do not expand coverage and create the illusion of corroboration where there is only repetition. Inspect sample search loops critically before using them in production. If the judge is inconsistent, the tree may overexplore poor branches or prune good ones too early. This is especially dangerous when relying on a single scalar score to rank close candidates. Structured scoring, calibration checks, and occasional human review matter even in inference time search. Test time search adds cost, so we need to know when that cost is justified. This part lays out the conditions that make search worthwhile and the trade-offs involved. Search is most useful when the task matters and the answer is uncertain. If the answer space is narrow and obvious, search is wasted. If the evaluation signal is weak, deeper search just produces more expensive uncertainty. The ideal case is a task where the model gets close but not reliably close enough, and a judge can meaningfully tell good branches from bad ones. That happens in planning, coding, structured reasoning, and bounded decision support. The real question is how much search to buy. A single-shot answer is the cheapest. Repeated sampling adds a breadth premium. Sequential refinement adds a depth premium. MCTS and ABMCTES add the overhead of maintaining a tree and using a selection policy to route compute intelligently. The more the task rewards careful comparison among alternatives, the more that overhead pays for itself. The less reliable the judge, the less likely the payoff is to justify the cost. For agent systems, test time search should be a configurable operating mode, not a default assumption. Alice does not need ABMCES for every question. It needs it when the decision is consequential enough that an extra few hundred milliseconds or several additional model calls are worth spending. This makes search a policy decision as much as a modeling decision. The engineering question is not just whether the model can search, but when the business logic should allow the system to spend additional inference budget. That is the central trade-off. Training time, learning changes what the model knows. Test time, search changes how much effort the system devotes to using what it already knows. Both can improve agent behavior, but they improve different layers of the stack. When the task benefits from extra deliberation, MCDS and ABMCDS provide a disciplined way to turn compute into quality without waiting for the next model release. The core idea behind our LLM is that the entire agentic workflow, not just a single model, can be the object of training. This section explains why that shift matters and how it changes what we optimize. In ordinary fine-tuning, we optimize next token behavior. But in multi-step agent systems, the real failures are often structural. A search branch is abandoned too early, a judge picks a weak candidate, or the workflow revisits dead ends too often. Improving the model alone is too narrow when the problem lives in the coordination between steps. RLLM makes a deeper claim than simply wrapping reinforcement learning around an agent. It says the routing logic, the solver role, the judge role, the search procedure, and the stopping conditions together define the behavior that matters. If the workflow produces the result the user experiences, then the workflow is what should be improved. It is closer to training a playbook than training a single move, though a playbook is fixed while this workflow can adapt through learning. Earlier methods in this chapter focused on improving a single agent's trajectories or tool calls. RLLM extends that to systems with multiple cooperating roles, branching, and pruning. It does not replace single agent RL. It absorbs those ideas into a larger object. This is the system-level layer of the chapter, not another isolated trick. This diagram shows the shift in optimization target. On the left, a single policy is trained. On the right, the entire agentic program, generation, selection, branching, and termination, becomes the object of learning. The arrows indicate that the workflow itself is updated, not just the model inside it. If the solver occasionally makes a local syntax error, a component-level update may suffice. But if the workflow consistently proposes good candidates, yet chooses the wrong one, or explores too little, or fails to combine critique with revision, then the failure is at the workflow level. In those cases, workflow-level post-training is the correct optimization target because the unit that must improve is the coordinated program, not one isolated model invocation. Single-agent reinforcement learning trains one policy to produce a sequence of actions. RLLM keeps that core idea, but changes what is being optimized. Instead of a single chain of decisions, the system now coordinates multiple roles that together produce a result. In single-agent RL, a policy directly maps to action sequences, and a reward signal updates that policy. RLLM keeps reward, trajectory, and policy updates, but the object being optimized is now richer. Instead of one policy emitting a single line of reasoning, the system may include several roles: a generator, an inspector, a selector, whose outputs feed each other. The trajectory becomes a coordinated program trace, not just a chain of tokens. This generalization is subtle but important. RLLM is not a separate species of learning. It is RL widened to cover a richer execution graph. The state is now distributed across the control flow of the program. A judge's choice changes what the solver sees next. A branch taken early changes the evaluation surface later. Because of this, the learning signal is often relational. A role is useful not only if its direct output is good, but if it improves the behavior of the whole coordinated sequence. This matters for credit assignment. In a single-agent setting, you can often attach outcome quality directly to a final action sequence. In a workflow, success may depend on the solver proposing a wide enough candidate set, the judge applying a consistent ranking criterion, and the orchestration layer surfacing the right branch at the right time. If the final answer is correct, it may be because several imperfect components compensated for one another. If it is wrong, the error may be due to interaction effects rather than any one component's local failure. RLLM exists precisely to learn in that setting, where coordination quality is the object of interest. A helpful mental model is that single-agent RL trains one player, whereas RLLM trains the whole team play. The analogy captures shared responsibility and coordination, but it becomes misleading if taken too literally. Workflow-level training still depends on explicit data structures, explicit execution boundaries, and a trainer that can turn runs into updates. The important lesson is not that the system becomes magical, but that the optimization surface expand from one policy's decisions to a composed program's behavior. RLLM makes the most sense when you separate two responsibilities: the workflow engine that runs the agentic program and the trainer that learns from its results. This split is the core architectural decision that keeps control flow reusable and learning logic independent. The workflow engine decides when to call the solver, invoke the judge, branch, continue searching, or terminate. The trainer consumes those execution traces, aggregates them, computes learning signals, and applies updates. This isn't just an implementation detail. It's the design move that keeps control flow reusable while letting learning logic evolve independently. Without that separation, a workflow becomes hard to reason about. If execution and learning are tightly interwoven, tweaking the update rule forces a rewrite of orchestration logic, and changing control flow risks breaking the training loop. Our LLM avoids this by treating the workflow as something that can be run, recorded, and replayed independently of how it's optimized. The engine does the work. The trainer learns from how the work unfolded, like the difference between a simulator and a learner in classical RL, but here the simulated object is a structured agentic program. This separation gives a clean boundary for experimentation. You can keep the same workflow shape while swapping the trainer's objectives, reward composition, or aggregation strategy. Conversely, you can keep the same training logic while changing the workflow to include a different judge, branching policy, or search-based subroutine. The same workflow object can be executed for inference, inspected for debugging, evaluated offline, and retrained later, all without rewriting its control flow. A second benefit is conceptual hygiene. Once the engine and trainer are separated, it's much easier to avoid conflating execution traces with learning state. The engine records what happened. The trainer decides how much that history should change future behavior. This distinction is crucial because terms like state, trace, checkpoint, and episode represent different layers. And RLLM uses the architecture split to keep them distinct rather than blurring them into a generic notion of context. A workflow in RLLM is just a class-use subclass, and the core logic lives in a single method called run. That method is where all the branching, selection, and termination decisions happen. At the end, the workflow returns an episode object that captures the entire trajectory, which the trainer can then use to learn from. The API is deliberately minimal. You write the control flow yourself inside Run, and the framework doesn't prescribe one exact coding style. What matters is that the trainable unit is explicit. The workflow is code, but it's code that produces a structured trajectory the trainer can consume. Inside Run, the program decides what to do next. A solver may propose a candidate, a judge may score it, and the workflow may keep the best proposal or ask for another. In search-heavy settings, Run might expand a tree and evaluate branches. In every case, the method is generating a trajectory that the trainer will later convert into a learning signal. This API shape makes clear that workflow is not synonymous with a fixed script. A static workflow has predetermined steps and no learning surface. A trainable workflow still has explicit structure, but the behavior within that structure can change because the trainer updates the policies used inside it. The code stays the same high-level program while the components improve. The exact framework details are less important than the roles of the parts. A minimal pseudocode sketch is enough to show the idea without pretending the abstraction is trivial. Here's the skeleton. The solver generates a candidate from the input state, the judge scores it, and the workflow decides which candidate to keep. The final return is an episode that packages the trajectory, reward, and outcome. The separation of responsibilities is clear: generate, evaluate, decide, and package. What matters in that sketch is the separation of responsibilities. The solver generates, the judge evaluates, the workflow decides, and the episode packages the experience. Because the control flow lives and run, the workflow can be inspected as a program. Because the output is an episode, the trainer can treat the run as a learning example. That is the bridge between engineering and optimization. The episode defines what counts as a single training example. It is the boundary that turns raw execution into something the trainer can learn from. While a workflow executes, the episode packages that run into a structured object. It records which decisions were made, what was observed at each step, which rewards were assigned, and how the run ended. This is the score sheet for the rehearsal. Not every trace is useful for training. A trace may contain verbose intermediate outputs, system messages, or tool calls. The episode distills that raw execution into exactly the form needed for post-training, keeping execution time, control flow, and training logic decoupled. A solver and a judge can participate in the same run, yet receive different rewards. The solver is judged on whether it generated a promising candidate, the judge on whether it selected correctly. The same episode supports different perspectives on the same sequence of events, making workflow-level training more expressive than simple input-output pairs. Execution produces an episode. The trainer aggregates episodes, and the update step refines the workflow's behavior. Over time, the system improves from them, targeting the solver judge, selection rule, or search behavior. The episode is the hinge between doing and learning. When a workflow has multiple roles, the hard part isn't just checking if the final output is correct. The real challenge is figuring out how to assign credit across the steps that jointly produce that result. Shared trajectories make this problem visible. A solver's proposal might only look good because the judge was able to discriminate well. Or a judge's success might only matter because the solver produced enough diversity to choose from. If the workflow succeeds, both components may have contributed. If it fails, the failure could come from poor proposal quality, weak ranking, insufficient branching, or an overly aggressive selection rule. The trajectory is shared, but the learning signal still needs to be structured enough to support coordinated improvement. This is the essence of system-level learning. Instead of updating each component as if it were independent, the trainer treats the workflow outcome as an integrated result. That could mean learning from a single episode where several roles interacted, or from a collection of episodes that reveal how role interactions affect final quality. The benefit is that the update reflects the system's actual objective instead of a simplified proxy. The cost is that credit assignment becomes more ambiguous. That trade-off is exactly why workflow-level post-training is useful. It makes the ambiguity explicit and gives the trainer a way to learn from it instead of pretending it doesn't exist. A practical way to think about this is that isolated component optimization asks, did this part do its local job? Workflow-level optimization asks, did the whole program behave well as a coordinated system? Those are related but not interchangeable questions. A solver can be locally competent and still sit inside a workflow that selects poorly. A judge can be accurate on individual comparisons and still fail to improve end-to-end outcomes because the search procedure never presents it with meaningful alternatives. When the dominant failure mode is systemic, optimizing the parts separately can leave the real problem untouched. This is also why the workflow abstraction is so powerful for agents that branch. Once a program can expand multiple candidate trajectories, the quality of the system depends not only on how good each local move is, but on how those moves are compared, filtered, and propagated. Shared trajectories let the trainer see that structure rather than collapsing it into a single final answer. RLLM uses that visibility to push learning up one level from the action sequence to the decision system that generated it. RLLM is not a replacement for ruler or art. It is the layer that absorbs them. Ruler provides judgment and reward machinery. Art shows how to collect, tool using rollouts, and train against structured tasks. RLLM generalizes that idea to entire workflows, treating those reward-bearing rollouts as components inside a broader trainable program. This progression is cumulative. First, the ability to score behavior, then to generate meaningful trajectories, then to train the workflow that orchestrates them. This layering prevents a common misunderstanding. RLLM is not introducing a wholly new learning principle unrelated to the methods that precede it. Instead, it recombines them at a higher level of abstraction. The reward signal may still come from a judge in the style of ruler. The execution may still involve tool using rollouts in the spirit of art. The novelty is that these ingredients are no longer used only to improve one policy at a time. They're used to improve the way the entire system coordinates those policies. RLLM asks not merely whether a model can act better, but whether the workflow that contains the model can become a better decision machine. A compact way to see the relationship is to imagine a ladder. Ruler gives you stable ranking and reward surfaces. Art gives you structured trajectories from agentic action. RLLM uses both to train the workflow that produces and consumes those trajectories. The latter metaphor shows dependency without implying replacement. Each step enables the next. None of them becomes obsolete because the next one exists. This is why RLLM is especially well suited to systems where the final answer is an emergent property of orchestration. A solver may be competent but inconsistent. A judge may be decent but need candidate diversity. A search procedure may be able to discover better paths only if the workflow lets it reuse internal evidence. RLLM's contribution is to make the whole stack trainable. The workflow itself becomes the object of learning, and the underlying components become participants in that larger optimization problem. This is why RLLM is especially well suited to systems where the final answer is an emergent property of orchestration. A solver may be competent but inconsistent. A judge may be decent but need candidate diversity. A search procedure may be able to discover better paths only if the workflow lets it reuse internal evidence. RLLM's contribution is to make the whole stack trainable. The workflow itself becomes the object of learning, and the underlying components become participants in that larger optimization problem. The solver judge pattern is the clearest illustration of workflow-level learning because it separates generation from selection into two distinct roles. A solver produces candidate answers, and a judge chooses among them or ranks them. In a static system, those roles are fixed, but in RLLM, both can improve together, making the workflow more than the sum of its parts. This joint improvement is especially valuable for reasoning tasks, where raw generation alone is not enough. The system benefits from multiple candidate derivations or partial solutions, and the judge acts as a filter that turns noisy breadth into usable quality. If either role is weak, the whole workflow suffers. Training them together aligns their incentives. The solver learns to propose candidates that are both plausible and discriminable, and the judge learns to prefer candidates that correlate with actual correctness rather than surface fluency. The solver judge setup is a perfect demonstration of shared trajectories and coordinated credit. The same run contains both proposal and evaluation, but the learning signal can be shaped to improve the interaction between them. This is a stronger claim than one model generating and another scoring. It says the program learns how to cooperate with itself. In production terms, this matters whenever the failure mode is not just generating a bad option, but generating too many mediocre options and choosing the wrong one. Joint training can improve both breadth and selection quality at once. One subtle but important point is that the judge is not just a passive critic. In a workflow-trained system, the judge becomes part of the behavior being optimized. That means its consistency, calibration, and selectivity all matter. A judge that is too lenient produces weak selection pressure. One that is too strict discards useful diversity. RLLM handles this by making the interaction learnable. The point is not to build a perfect critic by fiat, but to let the critic and the producer co-evolve inside a trainable workflow. One subtle but important point is that the judge is not just a passive critic. In a workflow-trained system, the judge becomes part of the behavior being optimized. That means its consistency, calibration, and selectivity all matter. A judge that is too lenient produces weak selection pressure. One that is too strict discards useful diversity. Our LLM handles this by making the interaction learnable. The point is not to build a perfect critic by fiat, but to let the critic and the producer co-evolve inside a trainable workflow. The 24 game packs the entire RLLM story into a small, well-defined puzzle. It is simple to describe, yet rich enough to reveal why workflow training matters. The agent receives a small set of numbers and must combine them with arithmetic operations to reach 24. On the surface, that is just reasoning, but underneath, it exposes a complete workflow. Generate candidate expressions, evaluate whether they satisfy the constraint, compare alternatives, and feed the outcome back into future proposals and judgments. The value here is not the puzzle itself, but how it makes the training loop visible. A solver can propose expressions that are close but incorrect. A judge can score or select among them. A successful workflow is not just one that finds a valid expression, but one whose search and selection behavior gets better over repeated episodes. Because the domain is bounded, you can see the mechanics without domain-specific distractions. The 24 game also shows why workflow-level post-training is broader than simply improving the final answer. Imagine two systems with similar final accuracy. One stumbles into solutions by accident. The other consistently produces better candidates and selects them more reliably. RLLM targets the second kind of improvement. It cares about the shape of the workflow, not just the endpoint. Robust systems are defined by repeatability, not occasional success. In the 24 game, repeatability emerges from coordinated learning. The solver's proposals become more informative. The judge's ranking becomes more discriminating. The episode-level reward captures the relationship between them. Over time, the system stops looking like a brittle one-shot answer generator and starts looking like a small reasoning program whose internal steps are themselves becoming competent. That is the essence of end-to-end workflow training. Our LLM extends beyond simple two-role programs. It also supports search-based workflows, including MCTS-style reasoning, which is essential for problems that require exploring alternatives rather than a single forward pass. The key insight is to treat the search tree itself as a structured workflow. Each node represents a partial state. Each expansion is a controlled action. Each evaluation is a judgment, and each selection decides which branch continues. This framing makes the entire search process trainable, not just the final output. Search and training serve different purposes but reinforce each other. Search spends more compute at inference to explore alternatives, generating richer episodes. Training then improves the policy or workflow so future searches become more efficient. The tree of explored alternatives provides far more learning signal than a single deterministic path. A practical way to think about this is as a trainable decision tree where branches are memoryless. The workflow learns which expansions and selections to favor. Some parts of the tree may rely on fixed heuristics, others on learned scores, and others on the solver or judge. Our LLM makes the entire structure available as a post-training target. A practical way to think about this is as a trainable decision tree where branches are memoryless. The workflow learns which expansions and selections to favor. Some parts of the tree may rely on fixed heuristics, others on learned scores, and others on the solver or judge. Our LLM makes the entire structure available as a post-training target. Training whole workflows introduces a stability challenge. Aggressive learning can cause a system to drift away from behavior that already works well, especially when multiple roles interact. KL regularization provides a guardrail against that drift by penalizing updates that move too far from the reference behavior. Think of the current workflow policy as a point in behavior space. KL regularization discourages huge jumps to distant regions where the model may become unpredictable. That matters more at the workflow level than in isolated training because the system's value often lies in carefully coordinated behavior. A solver and judge that worked well together may stop cooperating if one side changes too abruptly. The main lesson here is not the formula, but the role. KL regularization is the stabilizer that makes workflow-level post-training tractable. It acknowledges that the system should improve, but not at the cost of destroying the structure that made it work in the first place. In a workflow context, the objective is to improve a reusable program whose internal interactions remain coherent after training. That is why KL regularization fits naturally into the RLLM picture. The workflow is not an unbounded search over arbitrary programs. It is a controlled optimization of a known agentic structure. KL keeps the control intact, allowing the workflow to learn new habits while preserving enough of its original behavior to remain intelligible, reusable, and operationally stable. KL regularization fits naturally into the RLLM picture because the workflow is not an unbounded search over arbitrary programs. It is a controlled optimization of a known agentic structure. KL keeps that control intact, allowing the workflow to learn new habits while preserving enough of its original behavior to remain intelligible, reusable, and operationally stable. The decision to train a workflow rather than its components comes down to one question: where is the failure happening? If the system mostly fails because a single component produces weak outputs, component-level optimization can fix it. But if the failure is about selecting the wrong candidate, shallow branching, inconsistent role coordination, or a decision process misaligned with the task, then the workflow itself is the right target. That is the central judgment RLLM encourages. Optimize the playbook when the playbook is what is failing. There's also a maintainability argument. Training the workflow rather than rewriting it by hand keeps the control flow as a reusable artifact. You can execute it, trace it, evaluate it, and retrain it without inventing a new orchestration shape each time the task changes. This matters because agent systems are often built iteratively. Teams start with a static workflow, discover where coordination breaks, and then either harden the logic or adapt the learning loop. RLLM provides a principled route for the latter, treating the workflow as both stable enough to be a product artifact and dynamic enough to be a learning object. A good rule of thumb is that workflow-level post-training becomes especially attractive when coordination or selection quality dominates the error budget. If the system already knows how to generate plausible candidates, but does not know how to organize them, rank them, or refine them across steps, then training the whole workflow can outperform repeated component patching. The more the task depends on interdependent roles, the more natural it is to optimize the interaction among those roles rather than each one in isolation. That is the conceptual endpoint of this section. RLLM is not just another wrapper around agents, and it is not merely a name for adding RL somewhere in the stack. It is a framework for making the workflow itself a first-class learning target. Once that idea is clear, the rest of the chapter's methods become easier to place. Ruler supplies ranking and reward, art supplies structured rollouts, search supplies richer trajectories, and RLLM turns those ingredients into a trainable system rather than a fixed script. This figure shows the separation at the heart of RLLM. On one side, the workflow engine runs the agent program and records each episode as a trajectory. On the other side, the trainer takes those recorded episodes and turns them into updates that improve the workflow. The two loops, execution and learning, are decoupled, which is what makes the workflow trainable without rewriting it. Chapter Synthesis: Choosing the Right Improvement Lever. Restate the chapter's governing claim in operational terms. The central lesson of this chapter is that agent capability is not a single scalar property that rises automatically with model size. In practice, what distinguishes a brittle prototype from a capable agent is the combination of how it learns, how it searches, and how its control flow is organized. A larger base model can help, but it is only one lever in a larger system. If the agent repeatedly chooses poor actions, converges too quickly on weak plans, or fails to exploit uncertainty at inference time, the missing ingredient may be training dynamics, test time compute, or workflow structure rather than raw parameter count. This is why the chapter has treated the agent as a learning system, not merely as a prompt attached to a model. That framing matters because it changes how you diagnose failure. When Atlas Travel Assistant produces a plausible but shallow itinerary, the problem may be that the policy has not learned enough about trade-offs, not that the model lacks words. When it hesitates over a high uncertainty booking choice, the issue may be that the inference budget is too small to explore alternatives. When it gets trapped in a bad routing pattern, The problem may be the workflow itself, because the control flow is forcing the wrong sequence of decisions. In other words, the question is not only whether the model can answer, but whether the system can learn, search, and coordinate well enough to produce the answer consistently under realistic constraints. A useful way to remember the chapter is to separate what changes the weights from what changes the search path and what changes the route the system follows. Training time methods alter the policy itself. Test time search spends more compute to discover a better action sequence without necessarily changing the policy. Workflow-level learning changes the structure around the policy so that the system as a whole becomes more effective even if the underlying model remains the same. These are not competing philosophies so much as different places to intervene, and good agent engineering usually starts by identifying the cheapest intervention that addresses the dominant failure mode. Figure 3.17. The chapter's core distinction. Agent improvement can happen by changing the policy, changing the search path at inference time, or changing the workflow structure around the policy. That distinction also explains why the chapter moved from reinforcement learning vocabulary to ranking methods, then to search, and finally to workflow-level optimization. Each step widens the scope of what can be improved. At the narrowest level, you can improve a policy over trajectories. At a broader level, you can compare multiple candidate trajectories and use relative evaluation to guide updates. At inference time, you can search over branches before committing to an action. At the broadest level, you can treat the entire workflow as a learnable object. The practical lesson is cumulative. More capable agents are usually not just better models, but better systems built from these layers. Rebuild the shared vocabulary that connects training and inference. The chapter's methods all depend on a small vocabulary that is easy to blur if you move too quickly. A trajectory is the full sequence of states, actions, observations, and outcomes that an agent experiences while attempting a task. A rollout is one sampled instantiation of that trajectory under a particular policy or search procedure. A reward is the signal that says whether a trajectory or partial trajectory was useful, correct, safe, or desirable. Relative evaluation is the act of comparing one trajectory against another rather than scoring each one in isolation. Once these terms are separated, the chapter's methods stop looking like unrelated acronyms and start looking like different ways of generating and using feedback. This is also where the distinction between trace and trajectory matters. A trace is the record you inspect after the fact. What the model said, which tools it called, what state changed, and where the execution went. A trajectory is the lived sequence that may be used for optimization or evaluation. In a production agent like Atlas, a trace might help you debug why a travel quote was rejected, while a trajectory might be one of several candidate plans scored during training. They overlap in content, but not in purpose. One is an observational artifact. The other is a behavioral sample that can become part of a learning loop. Rollout deserves special attention because it is the bridge between policy and experience. The policy proposes actions, the rollout materializes them, and the resulting outcome becomes a candidate for reward assignment or comparison. That means agent training often does not learn from a perfect answer key in the way a supervised classifier might. Instead, it learns from sampled behavior, sometimes under uncertainty, sometimes under partial credit, and often with noisy or delayed feedback. The policy is shaped by what it actually tries, not by what an omniscient oracle would have chosen in hindsight. This is why the chapter emphasized sampled trajectories, group comparisons, and judged outputs. They're the raw material of learning in settings where direct labels are too sparse or too expensive. Inference budget is the other term that deserves to remain vivid. It refers to how much compute, branching, judging, and refinement you can spend when the agent is running. If training changes the probability landscape, test time compute changes how much of that landscape you are willing to explore before acting. That difference is operationally important. A system with modest training but generous search may perform well on hard, ambiguous tasks. A system with strong training but no inference time slack may still fail when uncertainty spikes. The chapter's core vocabulary therefore maps cleanly onto system behavior. Trajectory and rollout describe experience. Reward and relative evaluation describe feedback, and inference budget describes how much deliberation you can afford before the system must commit. Map failure modes to the layer where they should be fixed. A mature agent team does not ask only whether a result is good or bad. It asks what kind of failure produced the result, because that determines where to intervene. If the agent consistently produces low-quality plans, even after careful prompting, the policy may need to be improved through training. If the agent succeeds on easy cases but collapses on ambiguous ones, the issue may be insufficient search at inference time. If the agent follows an awkward sequence of steps that creates unnecessary risk or cost, the workflow may be misdesigned. These failures can look similar in a transcript, yet each points to a different layer of the system. This diagnostic frame prevents overreacting to the loudest symptom. A weak booking recommendation from Atlas Travel Assistant does not automatically mean the base model is inadequate. It may mean the agent is too eager to accept the first reasonable option, that it never compares alternatives, or that the workflow does not route difficult cases into a deeper planning path. Similarly, a support triage workflow may be making perfectly fine individual decisions while still underperforming because the handoff structure is misaligned with the types of tickets it receives. In that case, training the policy harder may help less than redesigning the routing logic. The chapter therefore suggests a practical hierarchy of fixes. If a cheap workflow change can eliminate the dominant failure mode, start there. If ranking multiple candidate outputs produces a clear quality gain without retraining, use relative evaluation before reaching for heavier optimization. If the model is fundamentally undertrained for the task distribution, improve the policy. If uncertainty at decision time is the bottleneck, spend more inference compute on search. If the problem is the control flow itself, redesign the workflow so that the agent is asked to do only what it can do reliably at each step. This is not a rule against model updates. It is a rule against using the most expensive lever before the simpler one has been tested. The deepest operational insight is that some bottlenecks are epistemic while others are structural. Epistemic bottlenecks arise when the policy does not know enough or does not rank actions well enough. Structural bottlenecks arise when the surrounding system does not expose enough alternatives, does not preserve useful intermediate state, or does not allow a better decision to be reached through the current route. One of the chapter's recurring themes is that these are not interchangeable. A bad policy can sometimes be rescued by better search. A flawed workflow can make a good policy look worse than it is. Effective agent engineering begins by asking which layer is actually failing. Summarize policy improvement through stable training dynamics. When the chapter discussed KL regularization, the point was not merely mathematical hygiene. KL acts as a stabilizer that keeps policy updates from drifting too far from a reference behavior. Without that constraint, optimization can chase short-term gains in a way that breaks previously useful capabilities, narrows the policy's support too aggressively, or creates brittle behavior that looks strong on the training signal but weak in real execution. The regularizer is therefore a guardrail on learning dynamics, not an ornament on the objective. It says that improving an agent should not mean erasing the useful prior that made the agent workable in the first place. The geometry of that idea is intuitive even without formulas. Imagine the current policy as standing in a region of behavior space that is already broadly competent. A large update can move it into a distant region where it becomes more specialized, but also more fragile. KL regularization makes that move expensive unless the new region is genuinely better according to the training signal. The result is not immobility, it is controlled motion. This matters especially for agents, because agents must remain coherent across many steps and tool calls. A policy that becomes overfit to a narrow reward signal can become worse at the long horizon behavior that makes the system valuable. GRPO and GSPO belong in this picture because they use relative comparisons to shape those updates. Their shared logic is that a policy does not need a perfect absolute reward for every action to learn effectively. It can learn from group structure, ranked outcomes, and comparative advantage among sample trajectories. That is especially useful when the environment is noisy, the reward signal is sparse, or the task is difficult to score directly. Instead of asking, was this single rollout good enough in an absolute sense? The method asks, which candidate performed better within a meaningful group, and how should that comparison change the policy? Relative ranking gives the learning process a more stable local geometry. The stabilizing value of these methods is practical, not abstract. Relative comparisons reduce dependence on brittle thresholding, and KL regularization prevents the update rule from exploiting quirks in the reward signal too aggressively. Together, they make policy improvement feel less like swinging a hammer and more like tightening a control loop. That matters for agent training because long trajectories amplify small mistakes. A tiny instability in action preference can become a large execution failure when the agent has to plan, call tools, recover from errors, and continue. Stable dynamics are therefore not a luxury. They're a prerequisite for making learning useful in systems that act over time. Show how ranked feedback becomes a training signal. Ruler, art, and hybrid rewards all answer the same basic problem. How do you convert judgment into something a policy can learn from when direct labels are incomplete or misleading? The answer is to score trajectories, compare them, and turn those comparisons into training input. The methods differ in how that judgment is formed, but they share the idea that a sequence of actions can be evaluated after the fact and then used to improve future behavior. This is especially relevant in agent settings, where the quality of a step often depends on what happened earlier, and where success may be visible only at the end of a multi-step process. Ruler is valuable because it replaces ad hoc metric design with rubric-driven evaluation. Rather than handcrafting a narrow reward for every edge case, you ask a judge to apply a structured rubric to the trajectory. That makes the signal more consistent, and often more scalable. Art then uses judge trajectories more directly as the substrate for improvement, which is attractive when you want the policy to learn from demonstrated process quality rather than only from final correctness. Hybrid rewards go one step further by combining deterministic checks with qualitative evaluation, allowing programmatic correctness to coexist with richer judgment about usefulness, completeness, or reasoning quality. The important practical point is that these signals are not interchangeable even when they are all called reward. A programmatic check is excellent when the task has a crisp answer, but can be too thin to capture process quality. A rubric-based judge can evaluate nuance, but can also be noisy, biased, or too permissive if left unchecked. A hybrid design can use the strengths of both, grounding the signal in what can be verified while preserving flexibility where the task is less discrete. This is why the chapter treated reward design as an engineering choice rather than a purely theoretical one. The more specific the task, the more valuable a direct check may be. The more open-ended the task, the more useful a structured judge becomes. The shared lesson is that judge trajectories turn ambiguity into usable supervision. In an agent system, the hard part is often not finding any signal at all, but finding a signal that aligns with the behavior you actually want. Ranking candidate rollouts can be more informative than labeling a single output because the comparison reveals preference structure. Mixed reward schemes can be more robust than a single scalar because they reduce the chance that the policy learns to game one narrow measure. In that sense, ruler, art, and hybrid rewards are not just training tricks. They are ways of shaping the feedback channel so that the agent can improve on behavior that matters in practice. Separate learning better behavior from spending more compute at inference. One of the chapter's most important distinctions is between training time improvement and test time search. Training changes what the policy tends to do. Search changes how much the system looks around before deciding what to do. Those are related, but they are not the same operation. A policy update is persistent. It affects future behavior across many inputs. A search procedure is temporary. It spends extra compute on the current instance, and then discards the exploration once an answer is selected. This difference matters because the right solution to a quality problem may depend on whether the issue is systematic or situational. If Atlas Travel Assistant repeatedly fails on a particular class of itinerary decisions, improving the policy may have the highest long-term value. If the task is rare, ambiguous, or expensive to label, however, it may be more efficient to keep the policy as it is and allocate more inference compute when hard cases appear. Search can expose latent capability that the base policy already contains, but does not reliably surface in a single pass. In that sense, test time compute is not a substitute for learning, but it can be a powerful way to harvest more value from an already competent policy without paying the full cost of retraining. The decision is therefore economic as much as technical. Training is amortized over future requests, but it requires data, infrastructure, and iteration. Search spends budget per request, which makes it attractive when the deployment volume is low, the task is high stakes, or the uncertainty is uneven. There is no universal winner. The right lever depends on how often the failure occurs, how expensive it is to fix, and whether the improvement should persist in the policy or only in the immediate decision. In production terms, the question is whether you want to buy a better model or a better answer path. This is also where the chapter's emphasis on better system versus better model becomes useful. A better model gives you improved priors. A better search strategy gives you better use of those priors under uncertainty. Many real agents need both. When the model is weak, search may simply amplify a bad distribution of actions. When the model is already decent, a modest amount of extra compute may unlock noticeably better decisions. The practical art is to notice which of those worlds you are in instead of assuming that every miss must be solved by retraining. Position MCTS and ABMCTS as structured uncertainty management. MCTS and ABMCTS are best understood as disciplined ways of managing uncertainty at inference time. They are not generic replacements for training. They are compute allocation strategies. The point of the tree is to turn a single-step guess into a sequence of tentative expansions, scoring, and pruning so that the system can inspect multiple possible futures before committing. That is especially helpful when a task has branching subproblems or when an early decision strongly affects later feasibility. A search tree makes those dependencies explicit rather than forcing the policy to compress them into one immediate answer. The value of this structure is that it makes exploration and exploitation concrete. Exploration asks the system to widen the search and examine alternatives that may seem less obvious at first. Exploitation focuses compute on branches that already look promising. MCDS formalizes the tension between those two behaviors, while ABMCDS adapts the balance to the quality and uncertainty of the branches encountered. The practical result is a reasoning process that is less impulsive than a single forward pass and more selective than blind enumeration. For agent systems, that selectivity is useful because compute is finite and not every branch deserves equal attention. ABMCES is especially interesting as a synthesis of search and judgment. When an agent like Atlas must choose among uncertain travel options, the search process can expand candidate branches, score them according to the evaluation rule, and then focus on the most promising states. This is not merely producing more text. It is a decision procedure that uses extra inference to improve confidence under uncertainty. The important caveat is that search cost grows quickly with branching factor, judge cost, and depth, so the method only pays off when the uncertainty is real enough to justify the extra work. Otherwise, you are buying deliberation where a simpler policy would have been sufficient. There is also a subtle but important distinction between search quality and search overhead. A method can be conceptually elegant and still be operationally expensive if the branch fan-out is too large, the scorer is too slow, or duplicate states are not handled carefully. In practice, structured inference is only as good as its implementation discipline. The chapter's broader message is that test-time search should be treated as a resource management problem, not a magical intelligence upgrade. It gives the system a way to be more thoughtful, but only by spending the budget to do so. Expand the lens from single policies to trainable workflows. RLLM extends the chapter beyond the idea of improving one policy at a time. Its contribution is to treat the workflow itself as a learning target. That matters because many agent systems are not a single model outputting a single answer. They're composed of stages, roles, routing decisions, and intermediate checks. Once you recognize that structure, you can ask a broader question, not just how should the model speak, but how should the whole system move from one step to the next? This is a major conceptual shift. A policy-level method improves the tendency of one decision-maker. A workflow-level method improves the arrangement of decision points, handoffs, and intermediate tasks. In the Atlas setting, that could mean separating research, comparison, approval, and booking into distinct stages rather than relying on one monolithic response. The benefit is that the system can be trained not only to answer better, but to route better, defer better, and compose better. The route becomes part of the learning problem, not merely a fixed wrapper around it. That framing makes RLLM a bridge between individual reasoning and systems design. It acknowledges that the control flow in an agent is itself an object that can be optimized through experience, judged outcomes, and reusable episode structures. For complex support or planning tasks, this is often where the biggest gains come from. A workflow that consistently sends ambiguous cases through a deeper analysis path may outperform a more capable but poorly routed model. Likewise, a workflow that preserves useful intermediate structure can make evaluation and iteration much easier, because the object of improvement is no longer an unstructured chat transcript, but a trainable episode with clear transitions. The broader lesson is that workflow-level learning solves a different problem from policy tuning. It does not just ask which answer is best. It asks which sequence of operations should happen at all. That is why the chapter treats RLLM as an expansion of the optimization surface. When the system becomes more complex, the relevant unit of improvement often becomes larger than a single completion. The workflow itself may be the source of inefficiency, and making it learnable can unlock gains that no amount of prompt refinement would produce. Give a practical selection framework for real systems. In a real agent project, the most useful question is not which method is best, but what kind of failure am I seeing, and what is the cheapest lever that fixes it? If the dominant issue is poor local decisions within an otherwise reasonable workflow, training time policy improvement is the natural first candidate. If the model is usually right, but occasionally fails on hard cases, test time search may offer a better quality-to-cost ratio. If the outputs are good individually, but the system routes work poorly, the workflow should be redesigned before the policy is pushed harder. If feedback is noisy, limited, or expensive, relative ranking and hybrid reward designs may provide a better path than trying to force a single perfect signal. A second axis is the availability and reliability of supervision. When you have clear, repeatable correctness checks, those should usually anchor the signal because they are cheap and hard to misinterpret. When correctness is partial or qualitative, judge trajectories become more useful, but they also require more care to avoid reward hacking or judge drift. Relative evaluation helps in those settings because comparisons are often easier to trust than absolute scores. If two candidate trajectories are both imperfect, a stable preference may still be enough to improve the policy. That is one reason the chapter gives so much attention to ranking and grouped updates. They're practical when clean labels are scarce. A third axis is latency and budget. Search and workflow branching both spend compute, but they spend it differently. Search concentrates budget on a single decision point, while workflow redesign may reduce wasted effort by ensuring the right steps happen in the right order. Training is more expensive upfront, but it amortizes across future requests. The cheapest acceptable lever is often the correct one if it removes the bottleneck without adding unnecessary operational burden. That principle is especially important in production, where every extra layer of orchestration, judging, or branching has a maintenance cost of its own. A fourth axis is complexity of implementation. Sometimes the technically elegant method is not the right first move because it creates too much integration work for too little gain. A relative ranking objective may be easier to adopt than a full search framework. A search framework may be easier to justify than a new workflow training pipeline if the problem is localized. The practical rule is to match the sophistication of the intervention to the shape of the failure. Overengineering an improvement path can create a more fragile system than the one it was meant to replace. The cleanest decision rule is to work outward from the observed symptom. If the model is weak, improve the policy. If the model is decent but uncertain, spend test time compute. If the control flow is wrong, redesign the workflow. If the feedback channel is noisy, use relative evaluation and stable ranking objectives to sharpen the signal. If the whole orchestration pattern is the issue, move toward workflow-level learning. That triage mindset turns the chapter from a catalog of techniques into a selection framework you can actually use. Figure 3.18. A practical triage flow. Match the observed failure mode to the cheapest lever that fixes the dominant bottleneck. Close the synthesis with trade-offs, priorities, and forward motion. Across all of these methods, the same trade-off reappears in different forms. Quality gains usually cost either data, compute, or orchestration complexity. Training improves the policy, but requires optimization effort and a reliable signal. Search improves the immediate decision, but consumes inference budget. Workflow-level learning improves the system structure, but increases design and maintenance overhead. Relative ranking and KL regularization make learning more stable, but they do not remove the need to choose where to spend effort. The art is to place the cost where it produces the most durable improvement. That leads to a pragmatic hierarchy. Prefer the cheapest lever that addresses the dominant failure mode, provided it does not introduce new safety or governance problems. Use ranking and judge trajectories when they give you a better signal than a brittle absolute reward. Use test time search when uncertainty is the main obstacle and you can afford the extra compute. Use workflow-level learning when the surrounding orchestration, not the base policy, is what needs to change. And when you do retrain, do it with stable update dynamics so that improvement does not come at the cost of fragility. This chapter closes with the idea that better agents are built by choosing the right improvement mechanism for the right layer of the stack. The next chapter turns naturally to model selection and trade-offs, because once you understand how learning, search, and workflow structure shape behavior, the remaining question is which underlying model family best supports those choices under real latency, cost, and deployment constraints.